All right, we'll start in a couple of minutes. If someone online could confirm that they can hear me, that would be reassuring and
We can
useful.
hear you.
Excellent, thank you. Great. Okay. Okay. All right, I think we can get started. Share my screen. Okay. All right, so welcome to this training organized by the Flemish Supercomputing Center in collaboration with the EuroC project, EuroC Belgium. Can I fiddle with the lighting for the slides? That would be convenient. Only I don't have a clue whether that's an option. That's maybe a bit harsh. Let's not do that. No, I don't really think that this is going to do anything. Okay, we'll have to live with it. All right, sorry, I'm not in the usual room I'm giving these trainings in, so it's a bit awkward. Okay, so let's continue. So the material for this training, including the slides, but also source code is available on GitHub. So this QR code brings you to it, but I'll also paste the link in the chat for the people online, since that's more convenient. There you go. So what you find there essentially is a small web page that just gives some details on this particular training. And most importantly, there is a link to the GitHub repository. As I said, it contains both the slides and the code, which gives examples a bit more extensive than the slides and lots of stuff that we can't cover anyway. So that would be the GitHub repository here. So yeah, it's pretty straightforward. Another thing which is useful is to follow us on LinkedIn for news on things related to high performance computing, to supercomputing, and to the trainings we give and so on. So it's always a good idea to connect. Okay, so this is a bit of a table of contents. I mainly generated this because I wanted to test Copilot in PowerPoint. So this is AI generated, I'm afraid. It should be more or less accurate, I think. Never mind. Okay, So let's start with a little bit of introduction. But perhaps before I dive in, let's start with a question. I'll start in the room, but the people online can also answer just using the chat. What I would like to know is your primary programming language. So, as you know, this is not a course on how to program. This is a course on how to program in C++, meaning that yeah, you are supposed to be able to program in something. And I would like to know what the something is. The reason I'm interested is that it allows me to give more context. So basically, if a certain feature is implemented in C++ and it differs in some way from your usual programming language, then I can point that out if I know what your programming language is. So I'll make the tour of the room and then I'll check the content of the chat in order to get an idea. So for you? Mainly Python? Mathematica. Oh, that's interesting. I haven't heard that in a very long time. And that's not negative. I really like Mathematica. Python? Okay. MATLAB? Sorry? Okay. Fortran? Oh, great. Okay. Sorry? Python. Okay. So a bit of a mix. Little bit of C, Fortran, mostly Python, and then a bit of MATLAB. Let's have a look online. So probably a similar mix. Someone already C and C++. Python, Fortran, Python. Okay. Python. All right. Happy to see that there are quite a number of people who actually use Fortran. There is some Java. Okay, so I'd say more or less the usual. Okay, so I will refer to differences with Fortran, with Python, a little bit MATLAB, and so on. So yeah, okay, that's good. All right, so maybe first some practical things. A recording is being made. That recording will be made available, if you like, to participants. If you like to have access to the recording, drop me an email and I'll send you the link. I do not publish these things publicly because I don't have your consent. Your name may appear in the chat channel that's not filtered. If I have to edit that out, that's way too much effort. I don't bother. So basically, participants can ask for the link to this to these recordings. So that's one thing. The other thing is the more interactive this is, the better I personally like it, and hopefully the more you will get out of it. So both for the people online and those in the room, if you have questions, please ask. For the people online, maybe first try the chat or indicate that you have a question. If it's too complicated to write out in the chat, I'll just ask you to activate your microphone. Okay. Yeah, that's, I think, it with respect to the practical stuff. So let's start with a little introduction and perhaps reasons why you might want to use C++ rather than some other programming language. And probably you have some reason to do so already because you're here. So, okay. I would argue that C++ is an interesting programming language for several reasons. First, its industrial strength. So many very important software projects, commercial products, are written and developed in C++. So that's already a good reason. So for those in academia who plan to go and work in industry, it might be a good investment to learn a bit of C++. Okay, I'm not in my presentation. Right. So it's a general purpose language. So it is not a language that's designed for scientific computing, as opposed to MATLAB, as opposed to Fortran, as opposed to Julia. Those languages have been specifically designed for scientific computing. C++ has not. So that means that sometimes it's a good match, sometimes the match is not that good. C++ evolves over time, and I'll mention a few things where it's evolving into a language that is more suited even for scientific computing than it is now. Okay, it is very feature rich. If you pick up a book on C++, the average book on C++, it will be like 1,000 pages. That's all very nice. There is a lot of legacy stuff there as well. So there are several paradigms in which you can program in C++. Obviously, object-oriented programming, because that was the main motivation for designing the language back in the 80s. But you can also do functional programming as well. And we will see some examples of that. I would argue that C++ has a very good standard library. It's called Standard Template Library. It comes with your compiler. And I would argue that this is really a very nice library. We'll see many examples of using the STL in scientific code. It does generate executables, well, the compiler does, that have very good performance on condition you know what you're doing. You need to know C++ pretty well in order to get good performance. So that is something that applies to many languages. With Fortran, typically you get quite good performance out of the box. With C++, you sometimes have to do a bit more work or to know what you're doing. Okay. The main drawback of C++ essentially is that, frankly, it's not an easy language. Let's be very clear up front. This is not really the most easy language you can ever learn. So basically, that may or may not be an issue. It also has a reputation of being a very difficult language. I would say that's undeserved. And that's for the same reason that, for instance, Fortran has not the best reputation. It's just because typically people are talking about versions of specifications of those languages of decades ago. That goes for Fortran. If you look at modern Fortran, it's a really nice programming language. Really, really. If you look at modern C++, it's very convenient to use, and we'll see some examples where actually the C++ code is not much longer, not much more verbose than the equivalent Python. So much depends on style, much depends on how you approach C++. So if you approach it as the modern programming language it is, the evolving programming language it is, then it's not that hard actually. Yeah, I can imagine that modern and Fortran for many people don't easily are put in the same sentence, but I don't agree. I mean, Fortran is really a very good language for scientific computing. It's designed for scientific computing. Arrays are first-class citizens. You can compute with arrays. It's easy. If you do that in C++, you have to revert to libraries and so on and so on, which means that in Fortran, the compiler can do much more, which means that out of the box, without having to think about it, you get better performance. Yeah, so basically, Fortran actually is a pretty modern programming language, and you can do happily object-oriented programming in Fortran as well, if you want to. So basically, for those interested, we have a MOOC on Fortran, so you can happily learn it at your own pace if you like. So, okay, but let's not go there. All right, so what's the scope of this training? Basically, you know how to program, you want to program in C++. So that's essentially the scope. Okay, there are a number of limitations. There are a number of things I will not discuss in this training because I deem them to be of less interest to scientific computing. So again, this is not a training course for beginners. You don't need to know any C++, but you need to know how to program. And also, the scope is mostly focused on scientific computing, which does not mean that you wouldn't learn quite a lot, which is useful in other contexts as well. But basically, I'm concentrating on a subset that I think is the most relevant for scientific computing. Okay, a little bit of history. So an important name in the C++ universe, multiverse, whatever, is Björn Stroustrup, who actually designed the language back in the 80s, so in 1983. So it's a fairly old language by now. It's 40 years old, 40 years plus old. Okay, so it has quite a history. And there are a few important dates, like 1998, which was the first publication of the standard of C++. So just like other languages, other programming languages, like for instance Fortran or C, C++ also has its specifications, which are the official specification of the language. So they define the syntax and the semantics of the language. And for C++, that includes the STL as well. That's part of that specification. So not all programming languages work in that way. They don't have a committee that sits and spits out specifications at the end of a week-long meeting. Basically, there are other models to let languages evolve. But okay, this is the one that C++ chose. So as you can see, after 1998, a lot of nothing happened. Well, okay, there was C++ 2003, which I omitted here. It was not so very interesting. But things started to pick up pace starting in 2011. And as you can see, there is a 3-year interval between releases of the specifications. So you got C++ 11, that's where things get interesting. And then C++ 14 made things a bit more convenient, didn't introduce many new features. Lots of new features in C++ 17. Then C++ 20. Okay, in theory, that should have been made life easier for stuff that was introduced in C++ 17, but lots of new stuff was introduced anyway. Same for C++ 23. And now, at this point, people are hard at work in order to define whatever C++ 26 is going to be. Now, if you look at the slides, you see that there is a fairly important caveat, not fully implemented yet. So there are two things. There is a specification, and that's a piece of paper, okay, PDF file. But at the end of the day, that's it. And then someone needs to implement all this nice stuff. And that implementation needs to be tested. That implementation needs to ensure that the code that it gets generated also has a little bit of performance, because otherwise it's crap. So basically that takes a while. And of course, there are these efforts are distributed. So that means that, for instance, certain compilers like GCC will first implement certain features. Other compilers like Clang will implement other features. They gain experience on how to implement them, how to optimize them, etc., etc. And then finally, everyone converges to support an entire standard. So what you can rely on is that for modern C++ compilers, choose your family, don't care which, C++ 17 will be fully supported. All C++ 17 features have been implemented. Most C++ 20 features have been implemented. Quite a number of C23 features have been implemented, but not all. And very unfortunate for us, one of the features which I'm really looking forward to is not implemented yet, except in some version of the Microsoft compiler, which unfortunately is totally and completely useless to me as an HPC person. But okay, you can't have it all. So basically, what we are going to, yep.
What is that feature that you're...
The feature is the multidimensional span. So basically to create a view on a one-dimensional array, which behaves as if it were multidimensional, which is of course in scientific computing pretty cool. But yeah, no one, okay, Microsoft. But besides Microsoft, no one has implemented it yet. Not even in the latest Clang, not even in the latest GCC. I would have to look at Intel, but given that it's Clang based, it would surprise me that they have it. Okay. So yeah, annoying. So mostly what we'll be talking about here is C++20 and some of the cute C++23 features that have been implemented and that are useful for scientific computing. So that gives you a bit of a yeah, where we are located in this history thing. And of course, we will dive into the STL as well. So the standard template library, which is the standard library for C++, if you like. Okay, so the presentation itself is based on a book, which I was very happy when it got published. This is the 22 edition. This is the last edition, the edition. It was published back in 2015, I think. So just when C++14 was released. And I was quite happy because it is a minimalist book in the sense that if you look at most books on C++, they will delve into features that are very interesting if you're into archaeology. So they list all the features that are still in there and that is best practice not even to know about, let alone use them. So this book, Tour of C++, was in fact the first book that said, well, okay, let's do away with all the historical ballast. Let's concentrate on what's relevant now. So in that respect, it was a very good book. And at that time, I was considering creating a C++ training, always hesitating because you always had this stupid historical legacy. And when I saw that book, I thought, okay, this is the thing. So basically, you will see references to the book throughout the slide deck. Of course, by now, because as you can see, the latest edition is 2022. So, of course, many features of C++ are not in the book, so they have been added in the slides. But at the end of each section, it's clearly indicated what I covered from the book. It's per chapter, what I added and what I left out. Because there are some things in the book which I think, okay, for scientific computing, it's not interesting. Yeah.
Will we also have a look at, let's say, the C++ ecosystem?
Yes, a little bit.
Referring to like in Python, NumPy, or SciPy?
Yeah, a little bit. Yeah, near the end of the training. So that would be next week somewhere. Yeah, indeed. So we will have a look at some libraries which you can use for scientific computing in C++. Of course, that's a very, very rich landscape and a bit more fragmented than its Python counterpart, in the sense that if you want arrays in Python, okay, there's not that many alternatives to NumPy. There are alternatives, but not that many. So basically in C++, you have quite a bit of choice. So I'll pick a few to discuss. And just by way of example of how you integrate external libraries into your applications, etc., etc. But of course, I can't cover everything. That's quite clear. Okay, so a few typographical conventions in the slides to make them hopefully more readable, easier to understand. Okay, this is HPC. So basically, yeah, you work in the shell and you do shell commands. So if there is a shell command, then that is rendered on a black background, and there's a $sign in front of it, just as a visual reminder, this is a shell thing, this is in the terminal. Of course, don't type the $sign, it's just, as I said, a visual reminder. Inline code fragments, file names, and so on are set in a monospaced font to make them stand out from running text. So hopefully that clarifies things a bit. And then longer code fragment, same font, but on a grayish background. So that's a longer fragment of code. If there are any data files, there won't be that many in this training, I think, but same thing, but on a slightly different color background. Okay, it's a little bit yellowish, I think. The projector is a bit odd here, but okay. So what you will see from time to time, unfortunately, is these ellipses. And that means not enough screen real estate in order to show the whole thing. So for code, that basically means we talked about this on the previous slide. We will talk about it on the next slide, or it's fairly straightforward. And in any case, any code fragment which is shown in the slides is always part of some full-fledged C++ file, which you can find in the repository. You will also notice that at the start of each section, there is a reference to the relevant directory or directories in the repository where you can find the code which is discussed there. Okay, before we continue, briefly something about vocabulary, because it's important. I will use these words quite a lot, and I do want to make sure that we are on the same page. So the words I will be using a lot are syntax on the one hand and semantics on the other hand. And it's useful that it's clear for everyone what that means, because I will use them quite frequently. So on the one hand, syntax, that's grammar. So basically, if you think in terms of natural language, that's basically the grammar of your language. If you think in terms of programming, okay, if your interpreter or your compiler gives you an error, that's a syntax error. Okay, so for instance, in English, it would be correct to say that a dog is barking. That is syntactically fine. On the other hand, the dog barking is not syntactically correct. That's not a good sentence. Okay, so syntax is easy. Syntax is something that you learn by heart. Syntax is something that your editor supports. Syntax is something that if you mess it up, the compiler will tell you, either clearly or a bit more obscurely, but yeah. So one of the things that you typically have to do when you start using a new programming language is get familiar with the bloody error messages that are spewed out by the interpreter or the compiler. That goes for any programming language. It's a process you have to go through. You have to familiarize yourself with the error messages. It's annoying, but yeah, that's life. Just like in Python, each successive C++ compiler tries to do its best to generate better and better error messages. It's work in progress, as it is in any programming language. It's not easy to generate good error messages. Okay, so syntax is easy. Semantics is a different kettle of fish. Semantics is meaning. So that is interpretation. And that is, of course, something that is mainly in your head, which basically means that a program can be syntactically correct and do the exact thing which you ask it to do, only it's not what you hoped it would do. But that's basically because there's some semantic problem. The meaning of what you write is not the same as the expectation that you have in mind. So basically, that's something to take into account. And if we talk about semantics in terms of natural language, then of course the dog barked is semantically correct, because that's indeed what dogs do. And the dog spoke would be incorrect, because dogs typically don't speak. The emphasis here is on typical, because semantics, crucially, depends on context. So there can be a context in which dog spoke, makes absolute sense, is semantically correct. For instance, in a fairy tale, dogs may or may not speak, but yeah, it's not unheard of. Okay, that's a very feeble pun. But anyway, you see where this is going. So semantics, it depends on the context. So that is an important distinction. And of course, the semantics errors are typically not caught by the compiler, because it's syntactically correct, and the compiler is concerned with syntax, not with semantics. Not entirely true. There are some flags which you can passed to the compiler so that it also does a limited set of semantic checks. And there are tools like linters and so on, static code analyzers, that will go a bit further. But again, it's heuristics. Basically, it's a set of rules, a minimal set of rules that are checked. So that's essentially the idea. Okay. So any questions up to this point? We didn't do any C++ yet, so probably not many questions. Okay, let's dive in. So this basically corresponds to the first chapter in a tour of C++. No, I don't have shares in the publishing company, but it is a nice book. And it's also a nice read, which is always a plus, of course. As you can see, code fragments are in the GitHub repository. Normally, this is the basics directory where most of the code for this chapter is. Okay, so essentially, this is the bare minimum you need to know to get some C++ application to work. So this covers quite a lot. It will cover basic types. It will also cover most of the statements. So this is pretty fast paced, but again, you know how to program, so that should not be an issue. Okay, of course, the example which is always given, which is not particularly scientific, is Hello World, but okay, you can't talk about programming languages and not mention Hello World. That's forbidden by the guild. So basically you have to do that anyway. Okay, so there are quite a number of things here, which we will discuss in detail later on. But this is a very minimal program, and as opposed to Python, where you can just run a script, for C++ you have to compile it. The compiler is going to analyze your source code. It's going to translate that into some internal representation, an abstract syntax tree, and from that abstract syntax tree, it's going to generate, probably with some intermediate steps, depending on which compiler you're using, machine instructions that can be executed directly on your target hardware. That's basically the idea. So the result of the input for a compiler is your source code, your program. The output is an executable, specifically for the target you compiled on. Okay. There are many compilers. So basically the most ubiquitous one, I'd say, is the GNU compiler. It's quite okay. It's quite feature rich, especially the later versions. If you pass the right flags, it has a quite reasonable performance. So it's definitely quite a good choice. There are alternatives. You have Clang, Clang++, which is basically an LLVM-based compiler. So it has a different backend, and it's also quite a good compiler. If you're on HPC, you can also use OneAPI. So the compilers that come with that. So those are compilers maintained and optimized by Intel, and they're also Clang based. So Intel takes the Clang base code and fiddles with it, mainly for performance reasons. So that is also quite a good choice. Okay, so those are, I would say, the main three. And then, of course, if you're on Windows, you can use the Microsoft compiler, which is quite good, but of course, in an HPC setting, who cares? Okay. So how do you compile? Quite straightforward. G++ is invoking the compiler. Then you can pass the standard flag, which basically says, well, okay, I want to compile this using the standard, in this case, C++14. Could be C++20, whatever, depends on your compiler, the version of it at least. So basically, that's something that you can check in documentation. There are a few other compile flags which are useful. --W all means enable all warnings. which is a big lie because they're not all warnings. There are some warnings, but whatever. Then another flag is -G. I'll discuss this in a minute. And then -O and the name of your executable. So -O, name of executable, that's an option with a value. And that's the name your executable will have. If you don't specify -O with the name of your executable, it will, on a Linux system, be a.out. Okay. There is a question in the chat. Okay, so basically, C++ is backward compatible. So essentially, I could put C++ 20 and be done with it, or C++ 23 even and be done with it. So yes, I can do that, but the question is, do I want to? Of course, compiling on the command line like this is something that you do for simple examples. If you're really starting to do something serious, you're not going to do this manually. You're going to use either CMake or make and basically let that do the build for you. And then the question is, okay, what do you target? And okay, what I typically say is, okay, it depends. Because where are you going to run your code? So basically, if you develop your code and you're using the latest and flashiest GCC compiler, then that would be 15.2 at the moment. And you would use a feature that's only supported by that compiler. So for instance, some C++ 23 feature, which happens to be supported in GCC 15, but not yet in 14. That's great. Up to the point where you want to run it on a supercomputer, where you have only GCC 13, and you've got a problem. So basically, it depends on who your target audience is. Where do you want your code to run? So it might be that you want to say, okay, I don't mind using the latest and flashiest features so that the code can be compiled, for instance, with GCC 12. So I just take C++ 17 and I compile with std C++ 17. If I accidentally use a feature that was introduced in some later C++ specification, the compiler will say, okay, no, can't do that. So it depends. For new development, I would say, okay, pick the specification of C++, the highest that you can get away with. And can get away with is then again modulo your deployment. So that's an important consideration. And that's why it may be useful to explicitly specify the C++ specification you're targeting. Okay. Frankly, I don't know what's the default because usually I have to switch it to something that's not a default anyway, like C++ 23 when I'm experimenting. So I would have to check what the default is. I don't know. Usually I just specify it. Well, I don't specify it. I specify it in my CMake file. So yeah, that's the answer to that. Okay. And then you have an executable. So you run your executable. Basically, I use the extension .exe typically for executables. As you know, under Linux, you don't have to do that. For my own executables, I find this convenient. It's easy to clean up, etc., etc. Okay, and basically that would work brilliantly. You would get "Hello World" on the terminal. Yes.
You have to name it .exe.
No, so you don't have to name an executable .exe. Actually, under Linux, Linux does not, well, almost never cares about file name extensions. So essentially, you do what you want. I emphasize almost always because, of course, there are some tools like compilers that do care. So in theory, You could write a C++ file and give it a name which does not end in .cpp or .cxx. And you can force the compiler to consider it to be C++, but okay, please don't. I mean, the whole tooling gets way too complicated. But apart from specific applications, typically Linux doesn't care about file extensions. It doesn't use them at all. Okay, so this is just for human consumption. To make it clear for me that this is an executable, then I see it at first glance that it is an executable. I don't have to ls-l in order to see that it has execute permissions, etc., etc. So that's all. That's the only reason. Okay, so let's break down those lines of code which we had for the hello world. So the first line is actually include IOStream. And that already starts bad because that's not C++. Okay. So that is a preprocessor, C preprocessor command. And what it actually does, more or less, not quite true, but okay, you can view this as a simple substitution. So the file IOStream just gets substituted into your source code at this location. That's more or less what it does. Okay, then where does that IOStream thing comes from? Well, basically it's a header file. I'll explain later in detail what header files are. Basically, they contain the declarations of stuff you want to use. Definitions, if you like. Not quite true, really declarations, but okay, let's not quibble right now. And basically, you can already guess what is supposed to happen because IOStream, IO means input output, obviously. So basically, this will have to do something to do with getting stuff on the screen, for instance. Okay. So the syntax hash include, this is a preprocessor keyword. We'll come back to the preprocessor later on. The bracket notation means this is an include file that comes with the compiler. The compiler knows where to find it. So this is a relative path, if you want. It's just the name of that header file, and the compiler knows where it is. Okay. So basically what it contains are in fact the declaration of stuff which we will need in our program. Okay, so a typical C++ program, the source code, starts with quite a lot of includes. IOStream if you want something on the screen or read something from the keyboard or do some file IO, whatever. And others which we will see later on what they do. Each C++ program, so each C++ application must have one and only one main function. So that's basically your entry point into the application. That's the function that gets executed when you run the application. One, only one, exactly one. So that's quite important. The name is always main, so you cannot change that. The return type is always int. You cannot change that. I'll explain why it's int, what you can do with that later on. And it can have either 0 parameters or it can have 2 parameters. That's it. The parameters are always, if you have them, are always int argc and character star argv array. Okay? Those represent the stuff which is entered on the command line. So the command line parameters. How to deal with them, we'll see later on. Okay, so basically this is a function definition. So no def keyword or anything. A function definition consists of essentially 4 things. The name of the function, in this case main. The type and names of the parameters, one or more separated by commas, and the return type, that's the int here, and the body of the function, which is now not shown, but basically that's the 4 parts that make a function definition. Okay. And then in the body of the main, we have two statements. This is one, that's the second. Okay? The first one may seem a little bit weird, but you see something called std cout. Okay? That's something to do with I/O. There's out there, so that's probably what makes the hello world appear on the screen. So indeed, std cout is an output stream. It's your standard output stream, and you send things to it. So this double less than sign is an operator. It's called the send to operator. So the string which comes after it here, hello world, is sent to standard output. And also the std end line, which is here, is sent to standard output. So the net effect is that on the terminal, hello world, exclamation mark, new line is printed. So that's the idea. Okay, so I can chain as many of these send to operators as I want, and you essentially read it from left to right. So first send hello world, then send end line. I'll detail the end line in a minute. So basically, if you have a function definition, each parameter must have its own type. So basically, if I have a function that takes two integers, let's call them a and b. So I would have something like, okay, int some function name, int a, comma, int b. So even though they share a type, they're both integers, I have to specify the type twice. Syntax, that's what C++ says. Okay. Important point about C++ statements, the semicolon at the end of a statement is required. It has to be there. If you leave it out, you get a syntax error. So that's different from Python, where you rarely use a semicolon at the end of a statement. You can do that, for instance, in notebooks to suppress output, things like that. But typically, you don't use semicolons in Python at the end of a statement. In C++, you have to. So both statements, both the std cout stuff here and the return 0 are essentially statements, so they have to be ended by a semicolon. Now, are programming languages that use a semicolon to separate statements? No, C++ ends a statement. And that's the same thing as you would do in C. So syntactically, there is zero difference here. Okay, so the second statement is a return statement. And that basically means that the value that the main function will return is going to be 0. Okay, the return statement, you know, it's the same thing as in Python. Fortran is weirdishly different, but okay, it doesn't really have that type of return statement. Okay, but essentially you use return for two reasons. One reason is you leave the context of the callee and go back to the calling context. So basically, it's a sort of sophisticated go-to in a way. And of course, it also gives the return value for the function. Okay. Yeah. No, because 0 is an integer. If I would put 0.0 there, it would be fine, because then the compiler would insert code to translate 0.0 into an integer 0, and that would also work. Would prefer not to do that, because yeah, it's more work for the compiler, it's more work for your code, for your executable, so I wouldn't do it. But yeah, normally it would still work. And with some luck, you would get a warning by the compiler that you are losing information, because you're narrowing from a float to an integer. So you lose the mantissa part, whatever the fraction part of your floating point value. So yeah. You hope that the compiler would say, okay, this is not a good idea. Okay. So something that's very important in C++ is namespaces. And everything in the standard template library, so everything in C++ standard library, is in fact in a namespace called std. Sometimes pronounced stud. Well, mostly I think in the States, but yeah, okay. So that means that stuff. I didn't talk about the end line. Maybe let me quickly talk about this as well. So basically, what that does, yeah, the name implies it will generate an end line, and that is going to be platform dependent. So on a Windows machine, that will be carriage return line feed. On Linux, Mac, and other sane systems, that would just be a line feed. So that's automatic. The compiler will ensure, or the standard library will ensure that on the platform this is compiled on, the right thing is going to happen for whatever definition of the right thing. And something else happened, and that's something that we need to discuss because it's very important for performance. Okay, so namespaces. So all this stuff, the cout and the end line and so on, they come from our include IO stream. So include IO stream contains quite a number of declarations of stuff in standard namespace, stuff which has to do with IO streams. Okay, so the reason for having namespaces is similar in a way to what you have in Python, for instance. If you look at Python modules, you can have multiple modules that actually define functions with the same name. Case in point, the math module in the standard Python library has a square root function. The CMath module for complex mathematics also has a square root function. Same name, different module. So you can sort of, not quite, but sort of conceptually at least, think of namespaces in those terms. They allow you to define variables, classes, functions with the same name in different namespaces. And you can easily mix and match those because you just prefix with the right namespace. So std for anything STL, something else for other libraries and so on. So that makes it easy to keep things separated. As I mentioned, it's similar to Python modules. It's not the same thing. So don't confuse a namespace with a module. It's not the same thing. But conceptually, you can think of it in those terms. Now, that basically means that in these header files, in the standard namespace, quite a number of things are declared, like for instance the cout and end line. Now, you are not obliged to use these prefixes. You can kind of import the whole thing by using namespace std. Okay, for those of you who are familiar with Python, that would be rather equivalent to from module, from NumPy, for instance, import star. Okay, don't do that. It's a very bad idea. So this is also a very bad idea. Don't use using namespace std, because that basically means that you import each and every variable, class, function, whatever that's defined in that namespace. I don't know what is defined, you don't know what is defined, nobody knows, and you will start generating potentially conflicts. Because you might define your own function with the same name as some function in std, and you get into trouble. So basically, in the slides, I'm very often going to assume that I did using namespace std. I never ever do that in production code. I only do it in the slides because of space constraints. If I have a line that contains 3 or 4 things that come from the stud namespace, that's 5 characters times 3 or 4. I mean, that gets wide. I don't have the space to do that. So in the slides, I'm very often assuming that somewhere near the top of the file there is a using namespace std. In the example code, unless I missed something, I'd have to check. But normally I never do this. I always use the std namespace prefix. You had a question, which I was ignoring.
Sure. If I do using namespace A and then using namespace B, does B overwrite A? Does that fail silently? Or does it
No, C++ rarely fails silently.
Okay.
It usually fails quite loudly. So,
Okay.
no, you would be aware. You would be aware. Yeah.
If there are private members in that namespace, are they also imported with this?
Basically, there is no such thing as private stuff in namespaces. So you don't control access through the namespace mechanism, as far as I know. Unless I'm very much mistaken, but that does not happen. If you want to use that kind of modularity, which is a very good idea, the problem is then you would have to use a fairly recent C++ concept introduced in C++23, which is modules. Problem is no one supports modules. Okay, no, not quite true. Actually, G++14 supports modules. Only CMake does it a little bit if you use the Ninja backend, which is not the default thing, which you have to install, etc., etc. So, okay, so modules are a feature that at the moment I'd not recommend, because if you, it will really complicate your build process. So that is unpleasant. It is the future of C++, so no worries. The tooling around modules will improve over time, but at the moment, it's certainly not there. I have an example in the repository of defining a module using a module. So if you're interested, you can have a look, but I'm not going to discuss it in detail. It's just too early. There is really no support around it. Even if it's implemented by a compiler, you need a lot of tooling to make it work. And the tooling isn't mature at this point. It's sort of there, but yeah, sort of not. Okay, so basically, if I do using namespace std, then I can just use cout, I can just use endline. Bad idea, bad practice, don't do that. What you can do is be a bit more selective. So just like you would do in Python, import something, from something import a specific thing. I could, for instance, say, okay, using namespace, stud cout. And then I could just use cout, but I'd still have to prefix endline with stud. Okay. So sometimes that can be useful. And in fact, C++ uses this in one of its standard template files. In the header for mathematics, this using something is implicitly included. So functions in C++, well, mathematical functions in C++ are not a language thing as they are in Fortran. They are a library thing as they are in Python. And so basically you have to use an include file in order to get their declarations. But although this is all defined in the stud namespace, you don't have to precede square root with stud, which makes a lot of sense because that would blow up your code and make it less readable. So that means that in the header there is somewhere a using namespace, std, square root, whatever. Okay. So a bit more detail about writing to a terminal. So basically that's writing to standard output. So that would be your sys std out. That would be your either unit 5 or the standard output unit in Fortran. So basically that is the same thing. All right, so everything regarding that is in IOStream. And basically, you have the destination. Where do you want to send stuff? And then the send to operator. And I can chain as many as I already mentioned that. Okay, so of course, in this particular case, I'm sending quite a bit. So in fact, remember, I had int main, int argc, and character star, argv array. So we'll get into the details, but basically argv is an array which contains, this hurt me to say it, but conceptually strings. It's something different, but okay, let's not niggle right now. And basically it will contain as its first argument the name of the executable. Again, not really true. And then as second, third, etc. arguments, the elements of that array, the things you pass on the command line into your application. So basically, here I'm assuming that I've passed at least one string on the command line, and that is the one I'm going to print. This already tells you, this fragment of code, that just like Python and C, that C++ is a zero-based language. So the first element in an array or an equivalent data structure will have index 0. That's weird for people who come from MATLAB, who come from Fortran, who come from Julia, from R, etc., etc. Mathematica, by the way. So basically it means that it's a programming language that has not been designed by mathematicians or physicists, because all those actually start counting from 1. If it's computer scientist, then they start counting from 0, whatever. Okay, that just as an aside. This also tells you, by the way, that string constants are delimited by double quotes. Okay, if you come from Python, you know that you can happily choose single quote, double quote, no one cares. In C++, a string is double quotes. Period. No discussion, no alternative. It's syntax, can't help it. So that's important to remember, because otherwise you get, well, I think you will get rather meaningful error messages actually, which you can actually figure out what's going to happen or what's going wrong. Okay, so this is a constant string, and then you send the value of this element of argv, so the second element of argv, and you send another string, and you send this end of line thing. Okay. So basically, that is how you do that. So command line arguments. Basically, in this case, I would call my application. Wait, what am I doing here? I can't read my own slides. That's the problem. It's too far away. Ah, yeah. Okay. So basically, I can't see the red there. There is dark red, which to me at least is somewhat invisible, but it's here. So basically that's command line argument. So if I call that with hello world, then if I do hello and then world, then hello world will be printed, or hello C++, whatever. So basically that's the way to get command line arguments in. However, the code is not exactly, yeah, the code is complete. You've seen it. Okay. So what might be a good idea is to, is everyone familiar with this? Or do I need to explain argv, argc in a bit more detail? Probably I need to for non-C programmers. Sorry? Yeah, so let me explain. Or let me show it, because basically it's easier to show this than to talk about it. So let me just go to the terminal here, and we go here. This is just some temporary directory in which I can fiddle a little bit. Okay, let's do CPP. Try to have a dot. Okay. So the first thing to do is include IOStream in main int argc star argv array. Okay, and let's just print stuff out. Okay, with some luck, and this is reasonable. Okay, let me quit this. Let me start Tmux, because then it's a little easier. Oh, no, that's not my plan. Okay, why did that change? Okay, that's better. All right, so let me again show the code. It was CLI. Okay. Yeah. Okay, I'll split vertically. Okay, so I need to compile this. Okay, it compiled cleanly, no errors. Yeah, I know I should add -w all and -w extra because all is not all, and w pedantic because, but anyway, and try to spell that correctly. So basically this is more and more and more warnings. This is what I usually put for production. So I'm pretty suspicious. I don't want any warnings. Sometimes I put a bit more, but okay, we don't get any warnings. So now we have cli.exe. If I just run it, you see that argc is 1 and that the value of argv0 is in fact /cli.exe. Okay, so I already lied to you as I indicated. Oh, okay. As I indicated, so argv0 is not the name of the program, but how you called it on the command line. Subtle difference, but sometimes it matters. Okay, and you have already guessed by now that argc is in fact a number of command line arguments, almost. It's actually the size of that array argv. Okay, so basically, if I call this with two arguments, with one argument rather, you see that now argv is 2, argc is 2, and argv1 is 1, etc., etc., etc. So you can think of the elements as of argv as strings. They're not really strings, they're actually character arrays terminated by a null character. This is inheritance of C, which really annoys the hell out of me, but that's how things stand at the moment, which really annoys me, because that means I have to explain C strings, and I have to explain raw arrays, which I don't like anyway, but whatever. Okay, so I think it's now pretty clear what this does. So basically that means actually just like in Python or just like in Fortran, if you want a command line argument and it represents a number, what you get is a string, you have to convert it to a number of the appropriate type. That's not a surprise, but it's also the case for C++. Okay. So that's the number of arguments, and that's the value of the arguments. Okay. So again, you can view argv as a, no, you cannot only view it, it is an array. So arrays in C++, starting index is 0. So that's 0 is the first element, 1 is the second element, etc., etc. Okay. Variables. Okay, you know what variables are. They are essentially a name for something that lives in the memory. So essentially a label for a memory location, if you want. Okay, names, as in many programming languages, start with a letter or with an underscore. So no difference there. They can, of course, contain digits. They can contain other underscores, etc., etc. So, of course, for a variable can change its value during the run. That's nothing spectacular. What you need to do is declare a variable. So that's a bit different if you come from a Python background. So in Python, you just assign to a variable and you're done. No, in C++, you have to first declare it. Basically, you have to say, you have to declare which type that variable will hold. And it will have that type during its entire lifetime. So a type is fixed as soon as you declare the variable. You can't use a variable that's not declared. That's the rule. It's the same as in Fortran. So basically, and declaration is quite simple. It's just the name of the type and the name of the variable. Okay. So here are a few examples. So I've got a variable with the name m, and its type is integer. Its initial value is going to be 13. So this is two things at the same time. It's on the one hand a declaration of m, so it specifies the type. It's also initialization of m. It gets the value, what is it, 13. Similar for n, so it's also type integer, and its initial value is 3 times m. This notation may seem a little bit weird. What you probably would expect, and which will actually work perfectly well, except for some minor details, is actually something like this. So this would work. It's fine-ish, but it's better practice to actually use the universal initializer. So this bracket notation is called the universal initializer, and it helps the compiler. Well, it doesn't help the compiler, but it forces the compiler to do some extra checks. So you will get some warnings in some circumstances when you use this universal initializer, while it would pass silently if you use the assignment operator. So it's a subtle thing, but I would recommend, since you are starting from scratch anyway, to get into the habit of using the universal initializer. So this, of course, only works when you also declare the variable. So this is declaration and initialization in one go, then you can use the universal initializer. Okay. Then here we modify the value of m, blah, blah, blah. I mean, that's not going to be very surprising, I guess. Okay. So notice that a variable declaration is a statement. So it needs to be terminated by a semicolon. Yeah.
When do you assign the memory? Is it when you declare it or when you initialize it?
It depends. So basically, in this case, it would be on declaration, even before you assign a value. And that is true for all static memory usage.
So it would sometimes be better to declare a variable, let's say, before a loop, and then update the value every time within the loop.
Compiler smart. So basically the question is, okay, so the memory for this integer, but okay, make it a somewhat more interesting data type, which is a bit larger. Is it better to declare it outside of a loop or inside of a loop? So that depends. If it's a fairly simple type, the compiler is going to be smart. It's not in every loop iteration going to use new memory. If it can figure out that it can reuse the memory it used on the previous iteration. So that's what I mean. If you have a reasonably simple type, this will definitely work. The compiler is more than smart enough to make sure that if you write the variable in the body, that is actually being reused between iterations, even if it's declared. So a good compiler will do that. Of course, if you have something rather sophisticated, where the compiler can't figure it out, then of course it's a different matter. But for instance, for numbers or for small things, it's not a problem. The compiler is more than smart enough. And actually, it's better style, because one of the things that you try to do is to limit the scope of variables as much as possible. The narrower the scope of a variable, the least room for trouble, subtle bugs, etc., etc. Okay. So the assignment operator is what you're used to. Just equality sign is the assignment operator. I don't think there's anyone surprised here. So okay, the R people might be surprised because you also have that arrow notation, but okay, regardless. Anyway, so of course, C++ is a typed language. So that means that I always need to specify the type of things. Not entirely true. We'll see exceptions because sometimes the compiler can figure it out by itself, but typically you declare the type. So here on this slide, we'll discuss some basic types, but there are many more which are interesting and which we'll discuss later on. I already mentioned that a string is denoted by double quotes. So single quotes are used for single characters. That's something that you don't have explicitly in a programming language like Python. Essentially, you don't have a type for character. It's just a string, essentially. Okay, byte code, yeah. You have bytes, but okay, let's not go there. So basically, in Python, you just have strings, essentially. In C++, you have a distinction between, on the one hand, an individual character, and on the other hand, a string. And individual characters typically are ASCII. So basically, you have a fairly limited set. You can use Unicode, etc., etc., but basically, a character itself is ASCII. Then the second type is string. So notice, this is a library thing. So a string is not a first-class citizen in C++. It's a data structure that you use out of the standard template library. So a constant string is delimited by double quotes. No surprises there. Just remember, you can't use single quotes here. If you do, it's a character. And neither of these things here, neither hello nor empty string, is a character. So compiler would complain, and you would have to fix that. Then you've got integers. So that's just the int type. And basically, yeah, there are no surprises there. Typically, an int is a 32-bit integer. So basically, that means that your largest integer is 2 to the power 31 minus 1. So that's 2 billion something. And your smallest is minus 2 to the power 31. Okay, so that is very different from Python and very different from something like Mathematica, where integers don't have limits. You can just keep on adding to a Python integer. It keeps on growing. As long as you've enough memory to store it, you're happy. Okay, probably not, but okay. But basically that means that's something to keep in mind, that there is a maximum integer. Now, of course, 2 billion is not that much. We'll see later on that there are other integer types, of course, that are a bit bigger. I'm not discussing them here, but discuss them later in more detail. Floating point is, of course, very important for scientific computing. So float in C++ is single precision. Float in Python is double precision. So don't get confused. A float in C++ is single precision. Single precision means 32-bit, 4 bytes, 7 significant digits, numbers up to 10 to the power 38. Smallest non-zero 10 to the power minus 38. So that's basically your range. Okay, and then you also have double. And double is then double precision. You've got 15 significant digits and numbers up to 10 to the power 308. So basically the two exist, and the two are basic built-in types. It's all ISO whatever, ISO 754 if memory serves. So basically you get the normal semantics of operations. A double or float can be infinity, it can be none, etc., etc. So normal behavior. Okay. So how do you write a double constant? Well, that's quite simple, as you would expect. How do we write a float constant? Well, similarly, but you have to append the f. So if you do not append an f, it's actually going to be a double. And that is something that can come and bite you, performance-wise. Not with respect to correctness, but with respect to performance, it can bite you quite a bit. So remember that that's a different thing. Okay, and then the last basic type is a Boolean. Values true and false. So lowercase as opposed to uppercase in Python. No dots as you would have in Fortran. Okay. Operators. So basically for int, float, and double, you can add them, you can subtract them, you can multiply them, you can divide them. One surprise, potentially, if you divide 3 by 5, you actually get 0. Why? 3 is an integer, 5 is an integer. In that case, slash is integer division, and integer division of 3 and 5 is 0. So that is something to keep in mind, and I really, really, really don't want to give a cent to everyone who messes up. 1 divided by 2, it looks so nice, and it looks like 1/2, but no, it's 0. So yeah, okay. So what I personally do, always, 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 if I write something that I intend to be a floating point value, I'll always use .0. So that It's a visual reminder for me, this is a floating point number. And second, I'm sure that the compiler is not going to use an inappropriate operator. Well, a very appropriate operator, except that I have the semantics wrong. So I would suggest that you consider that. If you have floating point numbers, just append .0. It's a visual thing, and you immediately see that is float, and no one gets confused. Okay. Then for integers, there is the modulo operator. So basically the remainder, if you divide. Nothing spectacular here. So for Booleans, you've got the logical AND, the logical OR, and the logical NOT. So double ampersand and double pipe. Maybe a bit weird. You actually also have single ampersand and single pipe, but those are bitwise operators. So they exist. You may or may not get a compiler warning, but they do entirely different things. So be careful here. Boolean, double ampersand, double pipe. Comparison operators, what you would expect. So double equality for equality, and then exclamation mark equality for different from. Okay. So slash equals in Python, Fortran becomes exclamation mark equal in C++. Okay. I'm mentioning float and double separately because, of course, the equality operator and the not equal operator are defined. But the question is, are they useful? And the answer is maybe not so much. Why? Because typically you get your floating point values as a result of some computation that is subject to round off. So even if mathematically your computation should yield equality, it might not. Case in point, if I compare 5 with the square root of 5 multiplied by the square root of 5, it's probably not going to be equal. Although mathematically, of course, 5 is equal to the root of 5 squared, square root of 5 squared. So that's why the triple question marks are here. That means that if you are inclined to write A equals B, and A and B are floating point numbers, step back and think whether that's really, really what you want. Most likely no. Okay. This is, of course, not specific to C++. It's just in any programming language except for Mathematica, because it has huge precision, no one cares. But basically, in let's say normal programming languages, you always face that issue. I do emphasize it because I see it regularly in production code, and yeah, that is not always a brilliant idea. Okay, so of course 1.0 divided by 3.0 is going to do the thing you probably have in mind. So basically that would give you 0.3333, etc., etc. Okay. And whether this is actually equal? No. Actually, most likely there's going to be a 4 here somewhere. So it's not equal. Okay, so mathematical functions are defined or declared in a header called CMAT. Okay, no, this is not complex mathematics. So in Python, you have the math and the CMAT module. So CMAT in C++ is the whole thing. So it contains the mathematics for real numbers, but also for complex numbers. And you've got all the functions you would expect, trigonometric functions, logarithms, exponents, blah, 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 the whole thing. Of course, you get quite a bit less than you would get in the as intrinsic functions in Fortran. But yeah. Okay. Then What you see very often in C++, and again, that's familiar to people who write Python, it's not so familiar to, for instance, people from a Fortran or a MATLAB background. So we have these shortcut operators. And of course, it's just syntactic sugar. So I can write the assignment of x plus y to y as x plus equals y. It saves typing. If your variable name is a single character, nobody cares. But if you have descriptive variable names, which are long, then of course this gets useful. You don't have to use this, but every C and C++ programmer does that. So you have to be at least familiar with it, with the semantics, so that you can understand the code. And that goes for all the binary operators. So for addition, for multiplication, for division, for subtraction, etc., etc. Same thing. That even works for logical operators. I could do ampersand ampersand equals if I want to update a logical value in place. Okay. As opposed to Python, we go a step further in C++. So n is equal to n plus 1 can be written as n plus plus. So that is something that in Python, unfortunately, you can't do, something I miss. But okay. This, by the way, is something that you don't have in Fortran at all. Okay, and similarly, the decrement operator. So plus plus is increment, minus minus is decrement. I don't think that's very surprising. However, they actually come in two versions. So I can do a pre-increment and I can do a post-increment. And the difference is subtle, but significant, and also sometimes very useful. Often it doesn't matter. Sometimes it matters quite a lot. So let's have a look at this code here. I've got a variable m, which I initialize to 3, and a variable n, which I initialize to 5. And then I do this. I add n++ to m. Okay? And then, of course, the question is, what's the output going to be? It's pretty clear, I think, that n is going to be 6. I think everyone will agree. Question is, what is m going to be when I print it? Let's have a look. Let's just run it. Well, we don't run it, but so basically m is 8. Okay. It could have been 9, but it's 8. Okay. This is a post increment. How do I know? Because the plus plus is coming after the variable, which it's incrementing. So post increment means use the current value, so 5, and then increment. So n's original value is used, which is 5. So n is going to be 8, and n is going to be incremented to 6. Okay. This is the other form, the pre-increment. So now the increment operator precedes the variable. So that means pre-increment, first increment, and use that value. So now plus plus n is going to be 6, and I'm going to add that to 3. So m is going to be 9. Okay? Yeah.
Does this have any functional use? Like, can the compiler use this to be more efficient, or just a short?
Okay. So is this useful? Does this have any functional use? Well, you give the compiler a bit more information, because the operation you're doing is really, really very specific. That's one thing. Another thing is that the standard template library overloads those operators from time to time, or okay, defines those operators for certain data types in such a way that pre and post increment do something else. So it may make a difference. Is that really functional? Okay, so you give you have two things. On the one hand, I'm wondering, I would have to check because I never really checked whether you could do that. But in certain for loops, you can use plus plus with an iterator. And I'm now really wondering whether I could use something like iterator plus equals 1. I don't know whether that's defined. I've never tried it because no one does that. But basically, it's not necessarily only a matter of syntactic sugar. It's also a matter of definition of operators. So the increment, the pre-increment and the post-increment are in fact operators, which means that in C++ you can overload them or redefine them or specifically define them for data types which you create yourself or which are created in the defined in the STL. Okay. So in simpler code, let's say the ordinary code, do you have to use it? No. Everything will work if you do it the Fortran way, n equals n plus 1. Okay. But you will see it everywhere in C++ code. Every C++ developer is using the shortcut. Okay. So choosing between post and pre-increment can sometimes be very useful. For instance, if you're doing arithmetic on array indices, then of course it makes a huge difference whether you use a plus plus I or a I plus plus. So that's an instance where you really have to think, okay, is this pre or post increment? Because if you use the one you don't want to use, the one with the semantics you don't have in mind, of course you get another array element than you might actually expect. And that's also something that you see quite a lot in production code. And if you see that, if you see an array index incremented in the square brackets, stop and think before you change anything. Because if the code is correct, the person who wrote the code thought about it. If the code doesn't work, it's a good place to have a look whether it actually does what the developer thought it should do, has done, blows up. Question?
Why shouldn't you just do that on the line before or the line after? So
because it looks so much nicer. Come on. Compare this. No, I'm joking, of course, but basically that is sort of what it boils down to. So it depends. Let me resize this a little bit. So it depends a little bit, of course, what you're used to and how familiar you are with things. But again, C and C++ programmers, suppose that I have an array. Let me just do it this way. A C++ programmer thinks that this looks way nicer than, for instance, and then using I. Okay. It's the important thing here, and of course I was joking, but the reason why I'm saying, okay, C++ programmers do this, C++ programmers do that, I do that for a reason. It's not just a joke. So basically, you will be part, as a C++ programmer, you are part of a community. And that community has certain conventions. It's the same in any programming language. If you write Python code as if it were C or C++, people are going to, let's say, developers with routine in writing Python will look at your code and step back and think, okay, this is weird. What's happening here? Oh yeah, that works. Yeah, it's even correct. Okay, great. But you don't do things as they expect it in the community. So that means that if someone is looking at your code and that person is a seasoned C++ programmer, and you do things in a way that is not done in the C++ community, although it's right, you are slowing that person down when he's looking at your code. You will see this thing, what? Ah, yeah, okay, yeah. In Python I'd also do it that way, something like that. So basically, that's the thing. Try to write C++ as a C++ developer. Try to write Python as a Python developer. Don't just translate one to one, because it's not going. It's going to feel odd to the other side. So that's actually an important point. And of course, if you come from a different programming language, that's not going to happen immediately. That's something that you grow into, but it's something that you have to be first open to and second attentive to. Pay attention to what the community does, learn the culture, because it's a matter of culture. It's nothing more than that. Sometimes good reasons to do things. For instance, you might have noticed, I didn't comment on it, but you might have noticed that in this for loop, I'll explain more about for loops, but you can already guess that this is going, this last part here, that this is going to increment the for loop iterator. And you notice that I use a pre-increment. Although it really doesn't matter. Whether I post-increment I or pre-increment I, nobody cares. For this loop. For other loops, which are not trivial, it does make a difference. It makes a performance difference. So that's why typically, if you look at most of my code, if it's not old, then you will see ++I in any loop. Why? Because for simple loops, it doesn't make a difference. For sophisticated loops, it does make a difference. So why should I stop and think if I can just say, okay, in a loop, I'm always going to use pre-increment. If it doesn't matter, I don't care. If it matters, I do the right thing. So it's one less thing I need to think about. Okay. Right. So a few general remarks. Okay, sounds silly for Python programmers, but C++ is a case-sensitive language. Fortran, MATLAB are not. So yeah, everything is case-sensitive. C++ keywords, variable names, function names, etc., etc. The whole shebang is case-sensitive. Statements always end with semicolon. Then comments. You have two types of comments. You have inline comments. That's a single line, and you start a comment by a double slash. Okay, you also have block comments, simple, /* closed by */. Nothing too strange, except for instance in Python you just have a single hash for commenting. So okay, that problem again. Okay, let's try and solve the audio thing. I'm going to try something. Normally I switch to the microphone of the laptop, but then I need to stand here, which annoys the hell out of me. I'm going to okay. So for the people online, is the audio better now again? Okay. So very weird, but okay. Now at least I know a fix that is different from standing. Oh, and now it's bad again, I guess. Okay, fine. Now at least I know a fix that doesn't oblige me to sit in front of that stupid computer the whole time, because that doesn't work. Okay, great. So two types of comments, line comments, block comments. Which one you use, I mean, it's all pretty obvious. Let's not comment on that. Okay, let's consider a small task. So basically, we've got a file, and that file contains coordinates, let's say. And one column represents X values, the other column represents Y values. We've got 1 point per line. That's the interpretation of this. And what we want to end up with is another file. And that file contains, again, numbers. And those numbers are the distance from the point in the corresponding point in data.txt to the origin. Okay. So how could we do that? So it's actually an excuse to introduce functions. So basically, we have a function definition here. And as I already mentioned, a function definition consists of 4 parts, if you want, or 2 parts, depending on your point of view. So the first part is the function signature, and that is basically its declaration. So its name, the type and name of its arguments, and the return type. So this also answers a question, or answers again, or illustrates the answer to a question I had before. So basically, I've got A and B, both are double. So you might think, okay, maybe I can write double A comma B. No, you can't. You have to write double A comma double B. Okay. So we compute something in that function, essentially the distance from that point to the origin. It's just simple computation. Note I'm including CMOD, so I can use square root. Okay, and then I return D. Normally, I wouldn't write it that way. Normally, I would just return the square root of, etc., not introducing the local variable D. But okay, this is just for illustration purposes. Okay, so basically the name of the function, argument types, etc. So no surprises there. And the implementation is, of course, the statements in the body. So the whole thing, the function signature plus the body, is the function definition. You can have a declaration only, and that is just the signature. So name, parameters, return type, followed by semicolon. No implementation. Okay, so that's declaration. This is definition. Sorry, seems nitpicking, but the distinction is quite important. Why? Because I can declare a function as many times as I like. I can only define a function once, and that has repercussions. It's something that the C++ compiler enforces. Okay, so basically, this is the function, of course, which we will call in order to get our data output. All right, so we have our distance function, and here you see I've got the declaration only. So it ends with a semicolon, no definition of the body. Then I have got some code, for instance, in the main function, where I use the function, I call it here with 2 arguments. And further down, so outside of my main function, I can actually define it. This is something that you see quite often in C++ code. You just declare stuff up front and you define it later on. That's weird, because that's not how things work in Python. Okay, what's going on? Well, basically, if you look at how C++ code is turned into an executable, that happens in several steps. I'll come back to this in details later on. So basically, first you have the compilation step. And that is essentially just generating local code. Now, what the compiler always does is read from top to bottom. What the compiler always expects is that what you use is declared. Okay, so if the compiler looks at the main function, it sees that a function distance is used. Okay, so it needs to be able to verify a number of things. It needs, at this point in the code, it needs to be able to check that this function dist exists. That's step number one, of course. Is it declared? So yes. It has two arguments, 3.0 and 4.0. Okay, those are double precision values. That matches the signature, the declaration. Fine. That is going to return a double. Okay, if I send a double to std out, that's going to work. So without knowing what this distance function is doing, the compiler can determine that this code is correct. And it can even create machine code for the main function. In the machine code, there will be a call dist. And at this point, it's just a call. So the compiler continues. And then later on, it sees this function definition. And it is going to translate that into machine code with bookkeeping, that when this is called, that is the machine code which should be called from that point. Okay, so that's why it's important to clearly realize the difference between declaration on the one hand and definition on the other hand. That's also why I'm typically emphasizing that if you include something like IO stream, that is the declaration of stuff. Because in those header files, typically, mostly you have declarations. Sometimes you have definitions, but mostly you have declarations. Okay. So function calls, I don't think there is anything surprising here. I mean, you can call it with literal values, you can call it with variables of the right type, etc., etc. So I'm guessing that this is not really surprising. Okay. Then, of course, important question, what do we have? For those of you who come from C, they know that C is always called by value. Fortran can do both, call by value, call by reference. By default, it's called by reference if you pass a variable. So what's going to happen in C++? Well, basically, you have a choice. This is an example of a function with call by value. So that basically means if I call the function with this variable n here, it's actually the value 5 that's going to be passed into the function. So there's no relationship between the function parameter and the memory location in the calling context where this value is stored. So that means if I change the value of n here in this function, then the value of n in the calling context is not going to be changed because those things refer to different memory locations. So the parameter n in the function, when it's called, just gets the value which is passed in. Okay, so that is going to be 5. Although here n did all kinds of things, but that was just its value, and coincidentally, they have the same name in the calling context and in the function. Okay. All right. You can do call by reference. So basically, this is another piece of code, another example. I've got a function swap, and that is going to take 2 arguments. And it's pretty clear that the semantics of the function is that it will swap the values of x and y. So when the function is called, I would like x to have the value of y the value of x. Okay. The logic here is pretty straightforward. The thing to notice is the ampersand here. So the parameters, the type of the parameters are not integers, but references to integers. So this is going to be a call by reference. That means that if I pass in A and B, that in fact the X here will refer to the exact same memory location as A refers to, and that that Y will refer to the same memory location as B. Okay, so that means that if I modify the values of X and Y, that will modify the values of A and B, because we're talking about the same memory locations here. Okay, more or less clear? So you do have a choice here. And you have to use this properly. Yeah.
Could you also say int temp is X?
Yes. So basically the question is, could I write int temp equals X? So with the assignment operator, yes, you can. But again, same rule. I prefer the universal initializer. So, but yes, it would work. And you will see that very, very often. Well, you will see that most of the time. It's only in, let's say, very modern C++ that people switch to the universal assignment operator. Okay. So a bit of a graphical illustration of this. So call by value. Basically, the blue thing here represents the memory of the computer, and we step through the code statement by statement. So if I declare and initialize A, then there is some memory location that A refers to, and that contains the value 3. Similar for B. And then we have swap. But note, this is a different version of swap. This has no references. So this is called by value. So let's see what happens. Well, if we call swap with as arguments A and B, then X and Y get the values that A and B have, but X and Y are different locations in memory. So we will get X and Y, which do have the values 3 and 5, but as you can see, they refer to something that is distinct from A and B. Okay, then we can start executing that function. Basically, we get temp, which also gets the value 3. And then we switch the values, we do some assignments, and as you can see, at the end of the function, indeed, X and Y have the values we expect. Of course, this has been an exercise in total futility, because as soon as the function ends, then of course, X and Y go out of scope, are removed from memory, and we're left with A and B having the same values as before. So this is what happens with call by value. And that's of course the default behavior, unless you indicate that you want call by reference. Okay. So same thing, but now call by reference. The only distinction is that now in my function signature, the parameters are references to int rather than int. And now we get something similar. We get 2 memory locations with 3 and 5. But now with the function call, X and Y refer to the same memory locations. We get the same thing, temporary for temp. We swap. But now, of course, that happens in the original memory locations. Swap ends and temp goes out of scope, but A and B have been modified. Okay, so that's a bit of a graphical representation of what happens. I often make this type of diagrams to explain these kind of things. It's pretty useful in my experience, but yeah, your mileage may vary. One of the things that I didn't mention, you see this return type here, void. Basically, that means it's a function that has side effects that doesn't return anything. Compare that to a subroutine in Fortran. Okay. All right. That is definitely time for a break because I'm actually half an hour overtime for break. So let's have a break now.
Okay, before we start talking about overloading. So let's perhaps take 10 minutes till 11:10. For the people in the room, you can get coffee. You can also get soft drinks. The coffee is for free. So if you get out of the room and you turn towards the entrance, on the right, you get into the entrance hall and you turn left into the cafeteria. You keep on walking and you walk onto two coffee machines. Feel free to use them. The coffee is for free. It will dispense a paper cup. Don't use the cups which are somewhere behind the wall. Please use the paper cups. Okay. If you want a soft drink, if you're in the hall again, entrance hall, you turn to the cafeteria. Don't enter the cafeteria. Turn right. There are vending machines. Those are not for free. Okay. Yep.
What time would you like to resume?
Let's say 1:15. That gives you 10 minutes and a little bit. Okay. I think I will get stuck in front of this stupid computer. Okay. So I don't need iron for certificates and stuff.
If not, let me know. For the people in the room, tomorrow we'll use Zoom 8, not only C. So if you before some training, for me it's nice to use because then I can use the microphone which is there. Now I have to use the microphone of my computer, which means I have to sit in front of my computer. And as you will Okay, just another thing for the people in the room. Did everyone sign the sign? Well, put his name on the sheet that is going around? If not, let me know. It's just for certificates. Okay. So thanks for letting me know that the microphone had issues again. I'll down in front of my computer, and then normally that should be good. The built-in microphone is actually pretty good. Only, of course, I have to sit here. Okay. So we talked about functions. Thank you. We talked about functions. And very important aspect is, of course, call by value versus call by reference. That's quite important. A thing which you can do in C++ that you can't do in C or that you can't do in Python is in fact overloading. So basically that means that you can have two functions with a distinct definition, provided that their signatures differ. To be precise, their parameters, types differ. So apart from that, they can do different things. They can even have different return types. They do have the same name, but they have different parameters and potentially different return type, and of course a different implementation. So that's something that's a little bit odd when you come from a different programming language, but it allows you to do really nice things. So here's an example. You've got the swap function, and it takes two int refs. So basically, it can swap two integer values. But of course, why would I only want to swap two integer values? I also might want to swap two double precision values. Okay, no problem. I can just define a very similar function. Actually, the implementation is the same in a way. The only difference is, of course, the type of the parameters, which is reference to double rather than reference to integer, and the type of the temporary variable in the function body. Apart from that, the functions are identical. Okay, so I can define both of them, and the compiler will use the appropriate version whenever the function swap is called. Or when I call swap with types that are not, for which it's not defined, of course the compiler is going to complain. So that's something that you can do in C++, and that's done quite a lot. So it's good to know that it exists, and it's good to exploit in your own code from time to time. Don't abuse this in the sense that overloading a function with something that does something entirely different, of course, is probably inviting trouble. So that would not be a good idea. Now, I have, of course, yeah, question?
Can you also overload a function only the return type?
No. So the question is, can you overload a function if just the return type is different? No, because the compiler doesn't have a clue what you intend. It cannot pick between the two types. It could potentially do that, but not in a safe way. Let's put it that way. I mean, you could implement something, but it would not make, it would be very dangerous. So no, that cannot be done. So the signature of the function must differ in the types of the parameters. That's the important bit. However, there is a remark here, because as you can see, those two functions are identical if I just replace the string int by double. Okay, so this is not by accident that I gave you this particular example. We will revisit this example when we talk about templates, and templates is C++ way to do generic programming. Okay, but that's for later. All right, functions, of course, can be recursive. That should not sound weird, but Fortran programmers know that that is something that in Fortran, at least, you have to declare explicitly. In C++, you don't have to. You don't have to do anything special in Python either. You can just call the function from the function body. No problem. So here's a not necessarily smart implementation of the factorial function. Okay. I don't think there are many surprises here. Of course, if you have a recursive function, remember you need a terminator. You need a terminating condition, because otherwise you get infinite recursion. Question?
Yeah, does the compilation catch the infinite recursion, or
No.
just keeps on compiling?
Yeah, no, it's not a matter of compilation. So the compilation will terminate, no problem. The code which is generated is going to be a function that keeps on calling that function. So you just get infinite recursion, you just get an infinite chain of function calls. And basically that is depending on where you're running, how the computer is configured, that is either going to be a segmentation fault at the end of the day or a stack error, depending on how the node is configured exactly. So bottom line, if you have a recursive function, if you define one, advice is first write the base case and only then do the recursion, just so that you don't forget. Okay. Of course, this is not specific for C++, this is for any programming language. All right, so then the question is, we had our task, which by now we've already forgotten, but the idea was we had a text file with 2 columns X and Y. Okay, one column representing X coordinates, the other representing Y coordinates. Each row represents a point, and we wanted to compute the distance from the origin to that point. Okay, so we already have our function distance. I think it was called dist, which does the computation given X and Y. So now we need to read that file, and we need to compute the result and generate the output. Okay. So we've got our function definition here, no problem. Then we have the main function. Note, this is the second form, the second signature, the second valid signature for main, so no arguments. So in this code, I'm not dealing with any command line arguments, so I don't put the int argc, int argv there. Character star argv there. Okay. All right. So I declare 2 local variables a and b, and now I'm actually doing a while loop, and I'm looping over cin std stud cin. So again, I've done a use namespace here, std. So normally in production code, I would always write std : cin. So what does this do? Cin, well, that sounds like input, and indeed, this is going to read input from the standard keyboard. So anything you type in will end up in stud cin. Okay. So you remember that for stud out, cout, we had the send to operator, less than, less than. Now we have the get from operator, larger than, larger than. So it points in the other direction. So I'm going to get stuff from stud cin, and I'm going to put it into A and B. That's the idea. So in other words, I'm going to read the string representation of 2 floating point values, and A and B will contain the corresponding floating point values. And I keep on doing that as long as I can read 2 string representations for floating point values. So this is the while loop. This is going to execute as long as this Boolean condition is true. And that expression is going to be equivalent to true as long as I can read. As soon as I can't read anymore, stud cin send to A, send to B, get from A, get from B, is going to evaluate to something that corresponds to false. Okay, then of course, in the while loop, I've got my values of A and B, and I can compute the distance to the origin. And I send that to cout, using the cout operator and end line. Okay. So let's do a little bit of code, because this might seem a little bit odd, but bear with me. Oops. Okay, better. So I'm going to include CMod because I want the square root. I want to include IOStream since I want C stat in, stat out. Then we've got double dist, double A, X, sorry, better name, double Y. Return square root X times X. By the way, I didn't mention it, but you probably already noticed, there is no such thing as the operator to raise a number to a power. So the star star of Python and Fortran, the caret of MATLAB, no, is it? Wait, what is it? Is it caret to raise it to a power? I think so, in MATLAB. It's a long time ago. I tried to suppress all memories of MATLAB. Sorry, bad joke. But basically, so there is no power operator in C++. So if I want to write a square, then I have to write X times X. Okay, yeah, as I mentioned, it's not a language designed for scientific computing. Okay, so in main, I need two doubles, A and B. And I need my while loop, get from, and get from, and cout. Okay. With some luck, that should compile. Who knows? It does. Okay, so how can I use this? Well, it's, I told you, standard C in, that's reading from the keyboard. Yeah. So great, that means that I can enter two values. And yeah, I get 5. Sounds good. And I can add other values. And I get something else. And I can terminate the input using Control D. If I'm tired of it, I can enter Control D. Okay. So great, and well, no, not so great, because what I wanted was a program, C++ application, that would take a file and that would spit out a file. And the only thing I have is a stupid thing in which I have to type in coordinates manually, and that prints to the terminal, and that's not files. Okay. So of course, if you're familiar with Linux, you know that actually we're done, because the only thing we need to do is use shell IO redirection, and we've got our file IO. Okay. If you don't believe me, let's do that. So I'll create a data file. Let's call it points.txt. And let's use similar values, so 3 and 4. So the values are separated by spaces, by the way. Let's say 1.3 and 5.7, whatever, and 0.6, 5, and minus 0.8, whatever. Okay, so I've got 3 points. Okay, so now how can I make sure that, what did I do? Something I didn't intend. So So basically, I can use my Brilliant application, and I use I/O redirection. So basically, I'm going to use the content of points.txt as if I were typing it into the terminal using the keyboard. So this is input redirection at the shell level. So now we are not talking C++, of course, we are talking Bash essentially. And as you can see, when I do that, you see that I indeed get 3 values, which are, with some luck, correct. So indeed, I can read from my file. I can also write to a file by using output redirection. So input-output redirection is a very nice tool in the shell. So basically, you can view that as arrows if you want, in a way. So basically, this guy says, use this as input, so it points to the application, as input for transform.exe. And this guy says, okay, the output, it points in this direction, from transform.txt goes into dist.txt. And as you can see, if I show you the content of dist, then you see that indeed it contains the 3 values. So this has nothing to do with C++. It's just that this approach, where you actually do file I/O based on standard input, standard output, without opening explicit files and so on, can sometimes be very convenient. And of course, this is the way that many Linux tools have been built. So this easily interacts with Linux tools. For instance, okay, this is not going to be very surprising, but if I compute the distances of these points, I can simply count the number of points I have with, or let me just do it this way, the number of values I have using WC-W. So essentially, it's very easy to build this kind of, no, I should not move. It's very easy to build this kind of Linux-like tools just based on your standard input-output, SDC in, SDC out, okay? So not particularly C++. The same thing applies to any programming language, but just to illustrate, because people sometimes don't realize that life can be extremely simple and that you can do file I/O without doing file I/O in your C++ code, just relying on I/O redirection in the shell. Okay, all right. Which does not mean that you can't do file I/O proper in C++. We'll see how to do that later on, but it's just that life can sometimes be much simpler than you might anticipate. Okay, so basically file I/O, or rather stream I/O. So essentially you read from standard input. So that would be your sys in Python. That would be your input unit in Fortran, or unit 5, don't remember the numerical value. Don't use it, so you shouldn't remember, but okay. So basically, you can also read from files. We'll see that later. And the operator you use is the getFrom operator. So that does, of course, quite a bit. It might seem pretty straightforward, but it does quite a bit, because what it also does is, depending on the type of the variable you are using, it's also going to do the conversion. Because remember, what you get with cin is just a stream of characters. So if you do a getFrom to a double, that means that that string representation, that sequence of characters, needs to be converted into a double precision value. And that's also done by the implementation of the getFrom operator. So it does also do the conversion. So that's reading from, writing to, you can write to standard output. Okay, that's the terminal. And you can, of course, write to standard error, which is also the terminal, but a different stream, the error stream rather than the output stream. And of course, similar for files. So basically, the operator is send to, and again, it does more than you might realize, because if I send a double to standard output, then of course that double precision value needs to be converted to a string representation, which again is done by that send to operator. Okay. So basically, that is what's happening under the hood. So this is the formal semantics of those operators. I'm not going into the details. If you're interested, you can read it, but yeah, I think you understand what it does. Okay. So we already used the while statement. It's not surprising for anyone in any programming language, I think. It does something as long as Boolean condition holds. That's it. So here's an example which will actually compute the greatest common divisor of two numbers. So as long as those numbers differ, you do stuff, and when they are equal, you found the greatest common divisor, and you're done. Okay, no surprise, I guess. Boolean condition, etc. So this, of course, is repeated 0 or more times. If the condition immediately evaluates to false, the while loop is not executed at all. So this is 0 or more. Why am I emphasizing that? It's pretty obvious, but there is a different statement, which is the do while statement. And the semantics is that this is executed at least once, and then a second time, a third time, depending on the Boolean condition. So while is 0 or more, do while is 1 or more. I note that it's less frequently used. I think in the whole code, in this repository, I use it once or twice at most. So sometimes it's quite useful, but yeah, very often you don't really bother. So remember, this is at least once. So that's the difference. Okay. The if statement, again, not many surprises. As opposed to Python, you really need to put the brackets there. The Boolean condition, that also holds for the while, by the way, the Boolean condition is always in brackets. Okay. So basically, Boolean condition is evaluated. If it evaluates the true, you get, otherwise you get else, etc., etc. So yeah, this is a bit boring, no surprises. So you can have, of course, an if without an else. That's pretty clear. And if you want to chain them, this is the syntax. So if, else, if. And that's, of course, again, different if you compare to Python, where you would have the elif. So here it's just else space if. In my opinion, actually a lot cleaner, because you don't have to remember the elif thing. Anyway, so this basically means I test this Boolean condition. If it's false, I test that Boolean condition. If that would be true, the next statement is going to be the one after the if, but yeah, I mean, you're familiar with that kind of thing. This is not a surprise. Okay. The fourth statement, I already used it when I illustrated the, I shouldn't move, when I illustrated the argv thing, argc argv. So basically, a for statement consists of a number of parts. So in the for itself, you've got 3 parts separated by semicolons. Okay. What's the semantics? Well, the first part here is a declaration or, well, it's an initialization, potentially with a declaration. So in this case, I declare variable I, and I initialize it to 2. The role of the I is, of course, the iteration variable. Okay, so this is done always and only once upon entering the for statement. So when I enter for, a new variable is created, I, and it will be assigned the value 2. Okay. The next thing that's done is with the second part of this for statement, the Boolean condition. So it's going to check whether that Boolean condition evaluates to true or not. So depending on the value of n, yeah, that will be the case or not. If that Boolean expression evaluates to true, the body of the for statement is executed. If it evaluates to false, we just go to the next statement. Okay, so let's suppose that I indeed is less than or equal to n. Okay, then the body of the loop is executed. So basically, value will be multiplied by I. Okay, and then the third part comes into play. Then we have this part here, the plus plus I. Okay, so plus plus I means, you know, increment I. Okay, so that's done after the body of the loop has been evaluated. So essentially it means, let's take a specific example. Let's suppose that n is equal to 4. Okay, so value is 1, I is going to be 2, I is less than 4. Okay, so we multiply value by the current value of I, which is 2. Okay, so value is now going to be 2. Okay, then we increment I, so I is now going to be 3. Okay, we evaluate the Boolean condition. I is less than or equal to 4, yes, because I is 3, and we multiply, we execute the body, so we multiply value by 3. So value is going to be 6. Okay, and then we increment I, so I is now equal to 4. 4 is less than or equal than n, so our Boolean condition is still true, so we multiply value by the value of I, which is 4, so we get to 24. Okay, value is now 24. I is incremented again. I is equal to 5. Boolean condition is evaluated. 5 is not less than or equal to 4. The for loop stops. We turn value. Value is 24. And fortunately, the factorial of 4 is indeed 24. Okay, so that's the semantics. Initialization executed once at the start of the for statement. Boolean condition checked before the loop is executed. Then execution of the body. Then increment. Repeat. Boolean condition, body, increment. Boolean condition, body, increment. Boolean condition false, stop. That's the idea. So clearly, I don't need a while loop, because any of these parts is in fact optional. So I could write for semicolon, I is less than or equal to n, semicolon, end of story. So that would be perfectly equivalent to while I less than or equal n. So in a way, the while loop is in C++, in fact, syntactic sugar. Of course, use a while loop when you intend to use a while loop. Don't write a massacred for loop, because yeah, that doesn't make sense. I mean, it's much clearer if you put a while loop there. But functionally, it's essentially superfluous. Okay, so how do you do an infinite loop in C++? Well, that would be And that's your infinite loop. So in Python, you would write while true. You can do the same thing in C++, but normally this is what you write if you want an infinite loop. Okay. And then, just like in other programming languages, you have a break and continue. So they have the same name in Python. They have the same semantics. In Fortran, that would be exit and continue. So exit is break, continue, cycle is continue. Okay, so what's the semantics? Basically, if I hit a break in an iteration statement, regardless of whether it's a while, a do while, or for, the iteration terminates. If I would have a nested iteration, so a for loop in a for loop, and I have a break in the inner for loop, only the inner for loop breaks. Okay, so that's important to keep in mind. Continue, so basically it means stop the current iteration and immediately continue with the next iteration. That's basically the semantics. So no surprises. How do you structure code in C++? Basically using blocks, and blocks are statements in curly brackets. So this would be a block. This would, oh, okay, this is by default sort of a block, but okay. So basically, this is a block. Blocks determine scope. So essentially, we can do very weird things. I can declare a variable I and assign 3 to it. That happens here in line number, in the first line. Okay. So of course, if I print the value, I don't think it will be surprising that it has the value 3. Okay, but now something odd happens. Now I start a new block because there are curly brackets here. That block runs from here up to the closing curly bracket, which is here. Okay, if I do a print of I don't think there's a surprise, it's going to be 3. Okay, but now I declare a new variable I, or I redeclare I, but remember that happens in this block. So now this I here is going to be this I. This I was the outer I. So if I print I would get 5 in this case. So I can redeclare a variable in a block, even if it already exists in outer scope. The compiler is not going to complain. Okay? This is an extremely bad idea. Don't do that. I mean, this is utterly confusing. So it's something that actually there is a compiler flag to warn against this. No, it's not in W-all, it's not in W-extra, it's not in W-pedantic as far as I know. You have to switch it on separately because, yeah, all and extra are not even enough. But basically, you can ask the compiler to warn against this. It's called shadowing. So this definition actually shadows the outer definition. Bad practice, don't do it. But you can do it. C++ allows it. Okay. Then a similar case, but a bit less or a bit more common, is actually that you say, okay, I have a for loop, and in that for loop, I'm declaring I and initializing it to 1. Oh, sorry, to 7 actually. So basically, this I here is a different I from that I, from the I in the same scope. So a false statement defines its scope for whatever you declare in the initialization part. And the scope of the declarations in this initialization part are, of course, the remainder of the for loop. So these parts here, and also the body of the for loop. So that begs the question. We modify I in this for loop. We start at 7 and we increment it to what? 9, 10? Actually to 10. So then the question is, what is going to be printed after the for loop executed? What's going to be the value of I? Note that this I has as scope everything up to the end of the file, unless you go into a block and redeclare the thing. So now there are two possibilities. Either after the for loop I is 10, or I is 3. It's going to be 3. Why? Because this I, scope of this I, is actually only the for loop. So suppose I would not have declared I here, and I would try to write I after the for loop, compiler would say, okay, I don't know about I. I is unknown. Okay? Yeah.
The first statement in the block wouldn't have been in the block. You have two variables declared with the same name in the same scope. Mm-hmm. Is it an error?
Yes. No, that's an error. So basically the question is, if you have a variable declaration and you redeclare the same variable in the same block, you get a compilation error. C++ does not allow redeclaration in the same scope. So in the same block, you cannot redeclare a variable. That's what I meant when I said, well, okay, for C++ variables, you have to declare the type, and that will be its type for the rest of the lifecycle. And the lifecycle of a variable is from the point where you declare it up to the end of the block in which you declare it. Or for global variables, which of course you never ever use, it would be to the end of the file. Okay. The outer one, no. So basically the question is, if I'm in the for loop, can I access the I which lives in outer scope? No, no, you cannot. It overshadows. This is again another example of shadowing, a bit less problematic in a way than the very artificial example with the block which we had here. This is really an awful idea. This, yeah, okay, I wouldn't do it, but if I were to see it in code, I could live with it. Let's put it that way. So in the for loop, it's a bit less dangerous, a bit less, but still it's confusing. So I would definitely not recommend it under any circumstances. But it's just to show you that you can do this and that it is a nice way to introduce bugs into your code. Obviously, yeah.
Maybe you may have stated this explicitly, and I missed it. I'm sorry.
Mm-hmm.
The scope of what's inside the for loop is, because you don't have a block, it's just like, it's just up to the first semicolon. Is that like?
Yeah.
We have like a.
So the question is basically, I do something here which I did not do up to now. So basically, I didn't, for the for loop, I didn't define a block, which is something that actually I never do. I always define a block. Okay, let me explain why. So basically, the question is, what's the difference? I'm just going to write some pseudocode here, so I don't really care. So I would have for int I is equal to 3, I less than 5. This is stupid, but whatever. So if I write this, I'm going to assume that there's a function f and that it does something meaningful. So basically, now the for loop will only repeat this statement. So if I would write g of I, then the only thing which is repeated is fi. So that's Pythonish in the sense of, or that is contrary to what you would expect in Python, where due to the indentation, you might expect that both f and g are part of the for block. And that's not the case. If I want that, I would have to define a block. And it would be like this. Okay, so if you have a single statement in your for loop, or your while loop, or your if, you don't have to use a block. You don't have to use curly brackets. My advice is do it anyway, because the probability that you will add a statement to the body of an if, or the statement to a body of a for is non-negligible, and you will forget to put curly brackets then. So typically my advice is put them there in the first place, then you can't forget them later on. Because typically those are bugs which are not easy to track. And yeah, I mean, if you can avoid them by simply using the convention that you'll always use a block, then yeah, that makes your life a lot easier. Okay. Now, actually, if no I is defined in out of scope, then actually this is not going to compile, because compiler is going to tell me, okay, I is unknown. You didn't declare that on this line here, on line 6, because I is only declared in the scope of the loop, and the scope of the loop extends from line 4 to line 5, does not include line 6. So the compiler will catch this. Okay, something I need to add a slide on, but I always forget to do it, so it will happen probably this evening on the train. You have something similar for the if. So what I can do is say if this does not make much sense as an example, but as you can see, the if part, well, the condition of what you put in the brackets actually can have two parts, where the first part is optional, because it was introduced only in C++17, so that's why it's optional, otherwise all the code would break. But basically, you also have initialization, and you have the Boolean condition. So the second part after the semicolon is the Boolean condition, as you know it from any programming language. The first part in front of the semicolon is in fact initialization. The reason why this was introduced is that now the scope of I is the Boolean condition and the body of the if and the else. So a while ago, I said, well, okay, in order to try and reduce the number of bugs, one very important approach is limit the scope of your variables as much as possible. If you don't need a variable unless at a specific position in your code, don't declare it at the top somewhere, because then its scope is the whole part. Limit its scope to where you need it. So if you need a variable only in an if or only in a for loop, declare it in that for loop or in that if. So that's basically the idea here. This was introduced, this grammatical construction, the syntax was introduced in C++17, so it's not that commonly used, but it's quite useful. And we will see a very good use case later on. Okay. Is scoping more or less clear? Yeah, question.
It's not about scoping, but just about C out.
Yeah.
In the one before last line, you don't put any end out.
Yeah.
And does this mean that the next line
yeah.
will just concatenate?
Yes. So basically the question is, and it's interesting because I've been using these slides for
a very long time. And actually, it's only this year that I get 2 remarks in a row about this, because I'm using the same deck of slides with regular students, and they also remarked on this, and you're perfectly right. So basically, I've got my C out here, and I put a space after each value which I output. So that means that the output here is actually 7 space, 8 space, 9 space. There is no end line which I output. So indeed, the output of this very last send to C out is actually going to be 3, which goes on that line. So the actual output would be 3 space, 8 space, 9 space, 3, and then a new line. That would be what really happens. I just didn't do that because it would mean an extra line, or having something weird like first here std C out, and then std end line, and then output I, and so on. So that would be a little confusing, and it's not the point I want to make. But you are perfectly right. And it's very funny because I indeed got the exact same remark on Friday. Yeah.
Is it equivalent to use NL or like the between brackets \n?
Okay, that's a very good question. And you've seen me do different things. So in the slide, you see std and L. In the code I typed, I used character \n. I've done that on purpose, not to confuse you, but to make a point. So the point actually is that end line, what I told you that end line does, is basically that it is going to produce either carriage turn line feed on Windows or line feed on Linux and Mac. So it's going to do the right thing for any platform. That's great. And if that were all would be nice. But of course, this is high performance computing. And in fact, endline does something more. So you might be aware how I/O works. So typically, if you write something to a file or you write something to the screen, what actually happens is that the output gets buffered. That's done by the operating system. So the operating system sees standard output coming from your application, and it's not necessarily going to put that immediately on the screen. It's going to wait until its buffer is full, and only then it's going to produce the output in the terminal. That's a standard behavior. Why? Because I/O is bloody slow, and if each time you write a character to the terminal, the operating system would oblige and put it there, your I/O would be very slow. So this buffering is a good thing. Okay. So why am I telling you this? Because endline, besides producing something nice for Windows and for other operating systems, actually also asks the operating system to flush the buffer. So to immediately produce the output. Okay. So essentially that means that if you have a tight loop, so a loop which is hot, which produces output, which doesn't do a lot of compute, but which outputs at a very fast rate, and you use endline, that means that for each iteration, you're asking the operating system, it need not comply, but typically it will, to actually put the output immediately on the screen, not using buffering. And your I/O will slow down dramatically. And of course, that part of your program is going to be excessively slow. So if you do file I/O, you can do this explicitly because there is a method called flush, and that is going to do the exact same thing. It's going to tell the operating system, now please write this thing to disk now. Again, it's a request. The operating system can say, no, I don't do it, but normally the operating system is going to do that. So basically, when you do I/O on files, it's perfectly under your control with flush. If you do I/O on std out or std cout or cerr, it is also under your control, but via the end line. So overusing end line in hot loops is a very bad idea. Don't do that. So that's why I'm typically nowadays, something that evolved over time, but nowadays I'm usually just using \n in all circumstances and only doing end line very deliberately. For instance, when do I want it very deliberately? Well, basically, suppose I have a loop. It's not a tight loop. So let's say I have an iteration loop, and every 1,000 iterations, I write progress to standard output in order to see where I'm, or to standard error, in order to see where I am in my program. So that happens every minute or every 5 seconds, almost the same thing. So in that case, I would really use end line for that output because I want it immediately on the screen. It's only once per 5 seconds, so I don't care. The performance impact is 0, I know that. But then it's a very deliberate choice. While in all other circumstances, if I don't care that the output appears immediately on the screen, why wouldn't I just use \n? The only argument could be that I want to maintain compatibility with Windows file formats and so on, but who wants that anyway? So who cares? It's HPC. But that would be another, that's another thing which you have to keep in mind, that, yeah, you won't get that automatically. If you want that, then either you have to configure it, which you can using some macro or a constant or whatever, or you would have to use end line, but then, yeah, you might take a performance hit. Okay. So that's basically the idea. Does that answer the question? That was a much longer answer than you actually hoped for, but okay. So is the problem. So it's more subtle than you might realize when you ask the question. So be careful with asking questions. You get more than you actually want. Other questions? Yeah.
There's no overload for end line that says flush is false or something?
No, not that I'm aware of. Not that I'm aware of. But of course, what you can always do is define, okay, you don't know what define a macro is, but let's say define a constant, which you change upon compile time, depending on whether you're compiling for Windows or for another operating system, and then use that constant as line ending. That would be the simplest thing to do at the end of the day. And that is part of what end line does anyway, be it under the hood somewhere in some header file. Okay. But indeed, good remark. So basically, this last tree is not going to appear on a line by itself. It's going to be concatenated to the previous line. Well spotted. Okay. So, of course, this is scientific computing. So we need arrays. Yeah, arrays we will have. That's not a problem. We will need arrays in order to represent vectors, matrices, etc., etc. Okay, this is not the way to do it. Don't use raw arrays in C++ code. There are much better ways to represent vectors and matrices. However, you do need to know a little bit about arrays anyway, because we already have been using one, argv. That is an array of strings, sort of, not really, but basically that's an array. So how do they work? Well, actually pretty straightforward. Basically, V would be an array where each element is of type double, and I've got exactly 5 of them. So the 5 is the length of the array, number of the elements. Okay? Don't confuse this with a Python list where you can keep on appending. That's not how arrays work. You specify upfront the number of elements you want to have. That's it. No more, not well, okay, you can use less, but then you do tricky things, but no more than 5 in this case. Okay, so this does two things. It declares V. It will also allocate memory. So this will make sure that somewhere in memory there is storage reserved for 5 consecutive double values. If you use arrays in C++, you know by semantics of memory allocation that these values will be consecutive in memory. So one after the other. First the one at V0, then the one at V1, etc., etc. No spaces in between or whatever. Yeah, okay, sometimes yes, but for simple types, no. So basically, that's the idea. And then, of course, you can use arrays, essentially, I guess, as you would expect. One of the things that you have to keep in mind is that arrays are really, really stupid in C and in C++. Okay, why are they stupid? Because at the end of the day, the only thing that V contains is the address of the first element. V has no clue about how many elements it has. Okay, that means that if you pass an array into a function and you want to do something with that array, then you would have to also pass to that function the number of elements of that array. So you get, from a certain perspective, very odd looking function signatures. You would get something like double A square bracket, empty, comma, int n. And n is then the length of that array. So there is also no way to ask for the length of an array, since the only thing the array variable contains is the address of the first element. Okay, that's the exact same situation as arrays in C. Do you want to go there? I don't, because this is lots of code which you have to, lots of things which you have to keep in mind in order to use something that should be a first-class citizen in a scientific programming language, which is an array, which is a multidimensional array. Okay, so clearly raw C arrays are not really the thing to use. So I'm mentioning them, but if you can avoid them, and very often you can, because there are other data types which are similar but safe and have proper semantics rather than this address thing, basically it's better to use those. So here you see an example of this function which does the sum of the array elements. So you pass in the array and you pass in the length, which means manual work. This is error prone because I do have to remember how many elements my array has when I call the function. Which means I need to define a constant for that, because otherwise, if I have a 5, I don't know what it is. So basically, you would have to define a constant for the length of the array, which then you pass into functions, blah, 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 blah. Very inconvenient. So yeah, it works. But if you want to use an array, step back and think whether you really need an array or whether you should use a different data type. And the answer is most likely going to be that you want to use a different data type. We will discuss these data types, of course, at length later on. Okay. Indexing is zero-based. I already told you. First element of an array, V0. Last element of an array, V. Number of elements, -1. This is also the reason why you will typically see this construction in C++ for a for loop that iterates over array elements. It initializes the index to 0, and then it iterates up to, but not including the length of the array. So this is the typical form of a for loop, the less than, I less than n, because n itself is the last element and then the next one. Okay, Typically, the compiler is also not going to warn you if you use an illegal index. So for instance, I can happily write v -1. I can happily write v17. Typically, the compiler is not going to object. With -1, it might. I don't know. I never tried, or didn't try recently. But for 17, probably not. If you use a linter, it will tell you, because those have logic to check for that typically. So what is going to happen when you use an array element, an index of an array element that does not exist? Well, it depends. Either your output is just garbage, or you get a segmentation fault. So if you're lucky, you get a segmentation fault, because then at least you know that something is wrong. If you don't get a segmentation fault, some value is going to be used. I don't know which one, you don't know which one, so you will get a random number. Maybe you notice, maybe you don't. Okay, so arrays are evil, typically, unless you use them in very controlled ways, and there are good use cases for them, but for scientific computing, don't. Bad idea. Okay, so yes, there are alternatives, no worries. Otherwise, we would stop here, go home, because then C++ would be uninteresting for scientific computing. So no worries, we get something in alternative to this. So there are many alternatives. Stat vector is one of them, but there are others as well. Okay, actually there are ways since C++20 to deal with arrays in a more safe way. Still, it's trouble, but it's a bit more safe. Anyway, I mentioned constants. So basically, if you declare a variable const, the compiler is going to check whether you attempt to modify its value or not. If you try, you can get a compilation error. So of course, as in any programming language where you have constants, which you don't have in Python, use const liberally. If something is not supposed to change, declare it const. Because then if accidentally you modify it, or some function might actually accidentally modify it, you will be warned. Well, you will get an error, to be specific. So that's, of course, good practice. So you can declare variables const. You can also declare parameters in functions const. So in this case, for instance, I could not modify n after initialization. Yeah. Sorry, I have to. Okay, I'll go back and ask the question. So basically, the question is, what should I use? Because this is actually the size of an array, and now I have in C++, I actually have two options. I can say, well, okay, this is supposed to be a constant, all right? So I can declare it as a variable, which is const, as in this case, const int, what is it, n, yeah, and initialize to 10. Or I could alternatively do this with a preprocessor macro. So define n 10. Okay. In most legacy code, you will see the preprocessor approach. So define n to be 10. Okay. What does that do? Well, basically, preprocessors are fairly straightforward. If you have define n 10, then any occurrence of n in your source code will be replaced by 10 before the compiler gets to see it. Very similar to what include does. It pre-processes the code before the compiler sees it. Okay. So basically, you would get a 10 everywhere. All right. So if I use const int n, 10, then the compiler knows that this is a constant, and it can potentially do a little more optimization here and there, because it has a little bit more information, because it knows that the n in one place is the same n as the n in another place. While if you just have the number 10, then yeah, okay, the compiler sees it's the same value, but the semantics is less clear from the point of view of the compiler. So in general, I'd say use const rather than macro preprocessor. It's also, yeah, in my opinion, more modern style. There are still use cases for the preprocessor, that goes without saying, but C++ is trying to eliminate it. So normally the preprocessor should go away and will probably be no longer required once modules are properly defined, properly supported, etc., etc. Then you don't really need the preprocessor anymore. And that's a nice thing, because then you decouple, then you don't have this extra step anymore. And the compiler can see everything as you write it without any rewriting of your code at an intermediate stage. But yeah, that's a bit of an opinion here. So don't consider this gospel. That's my take on macros versus const expression, etc., etc. The whole shebang which you have in modern C++. Modules, etc. Yeah, question?
If you have constant container types like arrays,
Mm-hmm.
is the constantness on the container, or does it also apply on the values
Mm-hmm.
in the container?
Yeah, that depends on the container. So basically for arrays, which is not a container, arrays is just an array, that's just, then it applies to the values as well. But for containers, you can actually choose. If you have a const vector, yeah, you have to initialize it and it will not have more elements, but the values themselves can change, except if you put const as values, and then the values can't change. So there you have the opportunity to fill and to see what you exactly need. So that's the answer to that essentially. So here, for instance, you would get a compile error because v is declared const. Okay. So these were the basics. Essentially, you could also more or less consider this as an introduction to C, because there are not that many differences between this part of C++ and C itself. What would differ is how you do I/O. In C, you would use functions like printf, fprintf, stuff like that, scanf, fscanf, rather than the streaming I/O. And of course, you can't do overloading, you can't do call by reference, etc., etc. But apart from that, things like if statements, while statements, and so on are very similar. The exception being that, as far as I know, but I would have to check C23, the if with the declaration part is not supported by C. But I'd have to check whether that's been added in the most recent specification. Okay. So all of this is actually not very interesting. Things get interesting at this point with user-defined types and so on. Before we delve in, any questions about the previous part? Yeah.
We have seen by value and by reference.
Mm-hmm.
Is there also a use case for by pointer, or is that
Yeah.
old style C++?
Yeah, so basically, very good question. For those of you who come from a C background, of course, you can simulate call by reference in C by passing a pointer rather than, so the address of something rather than the value of something. And that amounts to a simulation of call by reference in C. Okay, so indeed you can also work with pointers in C++. And yes, there are valid use cases, but if you have the option to use references, always use references. That's very simple. You do have pointers. We will see a couple of use cases for pointers. For instance, you will need pointers if you have a data structure such as a graph or a tree. Okay, you can implement them using arrays only, but okay, it's easier to work with pointers. And then you really need pointers. And you would also pass pointers into functions. But again, just like arrays are rather primitive, raw pointers in C++ are also considered rather primitive. So you have in C++ something called smart pointers, and those are much nicer to use for several reasons, which we will get into later. That said, there are still cases where a raw pointer is actually the thing to use, but then usually as a constant. And then it's just, then it has it's ownership versus usage, and then you have const usage rather than transfer of ownership. But okay, we get to that next week. Okay, other questions? No? Okay, so user-defined types. First, a bit more about types in general. So I said, okay, int is integer, and yeah, that's 32 bits, blah, etc., etc. Of course, you actually want a bit more control, and you also want a different integer type. So you also have long, and typically that translates to 64-bit. 64-bit will be enough. So basically numbers up to 2 to the power 63. You have signed and unsigned versions of both int and long, but there is an issue with int and long. So if you look at the C++ specification, and by the way, the same applies to C, what you will see is that it's never specified how many bits an integer or a long is supposed to have. The only thing that is specified in the specification is that the number of bits of an int is less than or equal than the number of bits of a long. Okay? So the specification is silent on the actual number of bits of these types. Now, in practice, I've never, ever, in my whole life, seen any system on which an int did not translate to 32 and a long translate to 64 bits. Okay? However, if you want to be really, really sure, actually, it's much better to use these types here, because those, of course, guarantee the number of bits. So the number here in int 16 underscore t is in fact a number of bits, so that's a 2-byte integer. So this is, of course, fail-safe in the sense that you know exactly how many bits you get, regardless of platform, regardless of compiler, regardless of anything. So this is, in fact, the safer approach if you care about the number of bits. Okay, and just as you have the unsigned versions here, you also have uint for everything. So basically, those are the unsigned values. Yeah, question?
Is there some speed improvement when we use the size speed versus the int?
So the size of, you mean?
Yes.
Yeah, so typically if you do size of int, you will get 4. Because the size of is computing bytes.
But, for example, if you use portable integers,
Yeah.
can we gain some speed improvements or?
Okay, so basically, if you use specific sizes of integers, can you get a speed improvement? Well, it depends. So basically, it depends on what you want to represent. Suppose, for instance, you've got image data. So you have pixels, you have an array, and each array element represents a pixel in your image. and say it's a grayscale image. Okay? Typically, grayscale images are represented by pixel values from 0 to 255. That's a typical thing to do. If you want color, no problem, then it's 3 of such integers per pixel, 1 for red, 1 for green, 1 for blue, but numbers between 0 and 255. Okay, that's great, because a uint 8t is going to exactly represent that range. The lowest value is 0, the highest value is 255. Okay, so if I'm representing image data, then uint 8t is a good idea. Does that gain me anything? Yes, it will certainly gain me memory. Because of course, if I represent my pixel as 3 uint 8 values, that takes 24 bits, 3 bytes. Okay, if I would use int, it would be 12 bytes, 4 times 3. So basically, I would gain memory. Your question was, will I gain speed? It depends. One of the things that you should realize is that for scientific computing, your performance bottleneck is most likely memory. Not memory in terms of how much do I have, but rather how fast can I get stuff from memory to the CPU. Because that's what needs to happen. All your data lives in the RAM of your computer. Before you can do any computation on it, it has to be transported from the memory to the CPU. Okay, that's governed by a couple of things. One of the things is bandwidth. The other thing is latency. Latency, for the moment, we don't care about, but bandwidth. That bandwidth is fixed. You can only transfer so many bytes per second. Okay, so if I represent my pixels as uint 8, or alternatively, I represent my pixels as int, essentially it means that my effective bandwidth, the number of pixels I get from the memory to the CPU per unit of time, is divided by 4. Because I can get 4 times as many pixels represented as uint 8 than I can if I represent the same pixels with int. So does that influence the speed? Yes, quite a lot. That may mean a factor of 4 in execution speed. So in that respect, yes, it matters which type you pick. And I'm now doing the whole discussion for uint 8 versus int, or uint 32, I don't care, whatever. But I can make the exact same argument for float versus double. If I don't need the precision, I can use float, and I can get twice as many floating point values from memory to the CPU per unit of time. My effective bandwidth is twice as large. Effective bandwidth defined as the number of things that I can get per unit of time rather than the number of bytes, because the number of bytes is of course the same for everything. But the number of things depends on the size. So since my float is half the size of a double, it means per unit of time I can get twice the number of float values as compared to double values. So again, if I don't need the precision, I'm better off with float. Also for different reasons. But that is one of them. Memory bandwidth, or effective memory bandwidth. Okay, does that more or less answer your question? Okay, probably also a bit more than you hoped for as an answer, but that is the point. There is a different side to that as well, and let me mention it right now, then it's out of the way. So besides memory bandwidth, there is another thing, and that is basically that if you operate on sequences of numbers, so essentially on arrays, which you happen to do all the time in scientific computing, accidentally or not so accidentally, then basically it's not the case that you just do, for instance, you add two vectors, let's say, very simple. Okay, conceptually, you think, okay, this happens element by element, and that's true. But in practice, that's not the case. In practice, depending on the type, whether it's float or whether it's double, you do that same operation. So adding vector elements, not on single elements, but on groups of, depends on your hardware generation, 4 or 8 double precision values, or 8 or 16 float values. So it takes the exact same time, more or less, to do 2 floating point multiplications, float multiplications, as it does to do 1 double multiplication. Not exactly 2, but okay, it's close. So basically that's factorization, and that's something that, at least to some extent, the compiler tries to do for you. There are ways to get that under control. If you're interested in that, there is a training on code optimization later on, and to really control the thing, you can use OpenMP, for which there is another training later on. But yeah, essentially that means that types matter. Types matter in the sense of how much stuff can I store in memory. But from a point of view of scientific computing, also important, or maybe even more important depending on volumes, memory bandwidth and factorization. So those are the critical things. And of course, smaller data types are faster. Smaller data types, in floating point terms, less precision. Can you live with it? I don't know. It depends on what you need. Can't tell you. But if you don't need the precision, don't use it. More memory for more precision, less performance for more precision. Simple. It's a trade-off. Okay, and the same applies to some extent also to integer types. You also have integer factorization, and of course the memory bandwidth argument is the exact same. So all of this applies not to individual values. All of this applies to operations on streams of data, so basically operations on arrays. If that's not the case, no one cares, because then you don't have factorization. The bandwidth issue goes away because you're just computing with single values. No one cares about bandwidth. Okay, so this only matters when you're operating on vectors, on arrays, on matrices, etc., tensors, whatever. Okay. All right. So real numbers, we already saw those, float and double, and then vectors and matrices. How do we represent those? Well, actually, in C++, you're somewhat spoiled for choice. So you've got the raw arrays. Don't use them. We already discussed that. So what's your alternative? Basically, there are at least 3 in the standard library. You've got stud array, you've got stud val array, and stud vector. So why 3? Because they have different semantics. They have different use cases, and they are not interchangeable. Some are, to some extent, but they serve different purposes. We'll see details later on, so don't worry about that. Okay. So basically, we are assuming, conveniently, that we already have solved the array thing with these standard library stuff. So, okay, we'll discuss that later, no worries. But what else do we need to define as standard, as user-defined data types? Well, typically, what you want to do is to define structures. So basically, you would have a struct, particle. That struct has 3 members, elements, attributes, vocabulary differs. Let's call it attributes. And for each attribute, you define its type. So it has an attribute X, Y, and Z. all of those are double. It also has an attribute mass, which is also a double, and it has an attribute int at a charge, which is an integer. Okay, so clearly this represents a particle that doesn't move, but that lives somewhere in 3 dimensions, which has a certain mass and a charge. And the charge is plus minus 1 or 0 or something like that. Okay, so if this reminds the Fortran people of user-defined types, yes, that's exactly what it is. It's almost the same thing. Not quite, but almost. So for Python people, yeah, this is a tuple, essentially, or a class. Okay, so each member, each attribute has a name, and each attribute has a type. Okay, so members, as you can see, can have distinct types. In this case, we have 4 attributes that are double, and 1 attribute that is int. So you can mix them. The order in which you do that does make a difference. So if you use this in an array, you have to take some care. That's why Fortran has a special keyword sequence in order to ensure that you get what you want. In C and C++, it's the order in which you define stuff. Okay, code optimization for details. Okay, so how do we use that? Well, basically, you define the struct, and then you can define a particle, and you can initialize it, for instance, immediately like this. So basically, the 3 coordinates, the mass, and the charge. So again, universal initializer, the square brackets here. Sorry, the curly brackets. Okay, so of course, particle 1 is not initialized. So its coordinates, x, y, and z, nobody knows. Whatever is in memory at the location that P refers to. Okay. Okay. So using the variables, P1 is such a particle. I can do P1.x. So that gives me access to the x attribute of this struct. And I can assign to it, or I can use its value. This is quite natural, I think. This is... In C++, you would use named tuples for this, or a class, whatever. But basically, it's the same thing. Most programming languages have similar concepts. User-defined types in Fortran, structs in C, same thing. Okay, almost. In MATLAB, you also have something like that, but I don't recall what it's called. Okay, cells or something a bit bizarre, but okay. Okay, can you pass that to a function? Yes, very naturally. You can just declare a function that in this case takes 2 particles as input, as parameters, P1 and P2. And what it is going to do is it's going to compute the distance between those 2 particles. So it's just Euclidean distance, no surprises. But given that I'm not intending to change P1 and P2, I declare them const. Okay. And you notice something else. This is weird, because there is this reference thing. So I don't pass in particles, I pass in references to particles. So normally, up to this point, I do that to get call by reference, so that I can actually change arguments, parameters in my function. But now I declare a const reference. So I can't change it. So why on earth am I defining this as call by reference? If I then declare explicitly that I really don't want to change it, why not just call by value? Would be much simpler. I could leave out the const, I could leave out the reference. So what the heck? Any ideas?
To avoid copying.
Indeed, to avoid copying. Because if I do call by value and I have a non-trivial data type, then the value of the original is going to be copied to the memory location for that parameter in call by value. I will get a copy. I don't want a copy because copying takes time. So that's why I pass by reference, because then that means that my function is going to operate on the same memory locations as my data is, no copying, and not changing it because I declare it const. So this is something that you will see quite a lot in C++ code, a reference to something const. That makes sure that no copy is created, saves time, saves memory, and safety net, I can't modify the thing because I declare it const. Okay, so this is something that you see a lot. So in this case, I have a move function that takes a particle and that takes some distance for x, y, and z in which it should be moved. So basically here again, we have a reference to particle, but now in this case, it's a quote unquote classic reference in the sense that I do want to modify the particle I'm passing into my function. So of course, in this case, no const. All right. Okay. Again, a void function. So basically, this is a function with side effects. It is not going to return anything. So the return type is void. Equivalent to a subroutine in Fortran. Okay. So basically, this is an object-oriented language. So you expect classes. Okay, we are done because a struct is a class. In C++, classes and structs are almost the same. What's the difference? Well, the difference is quite simple. In a struct, by default, anything is public. In a class, anything by default is private. That's it. That's the only difference. Okay? This is interesting because if you look at modern C++ code, you will see very little class and you will see mostly struct. If you look at older style C++, you'll always see class rather than struct. So that's a bit of a historical shift, and it allows you to sort of date the code you're looking at. So typically nowadays, I hardly ever use class. I'll always use struct in order to define a class. So basically, it's easy to use a struct or a class. We've already seen it, how to do it. So it's quite easy. And of course, it's good to model something in the sense that if I would have to operate on a particle and I wouldn't create a struct or a class, I'll use the word struct, but I mean a class, then what would I have to do? Then I'd have to pass in the position of a particle and its mass and its charge, and there would be separate arguments to functions. So basically now I have the concept of a particle. So all the properties of the particle, all its attributes are in the particle itself. So it's a way of modeling things. Why am I saying that explicitly? Because at least with regular students, okay, they don't know how to program. They learn programming using C++, but they're scared of structures for some reason. But yeah, I suppose that's less the case for you. Okay, so basically, I already mentioned this, classes members are private by default, and that's the only distinction. So whether you use class, whether you use struct, doesn't matter, as long as you control the access appropriately.
Why this shift from using classes to struct?
I don't know. So the question is, why did people start using struct rather than class, while they did that in the past? So why they did it in the past, I can tell you. Because basically, the idea was that to make a very clear distinction between a classic C structure and a class. That was also why the keyword was introduced back in the 80s. But given that then structs could act as classes, my guess, but this is purely a speculation, is that people just want to reduce complexity. If you can do it with one keyword struct, why use another one as well, which does almost exactly the same thing. So that's probably why it's shifting. But that's the only argument that I can give you. I've never discussed that with people who are, let's say, on the standard committee or anything. So I can't give you a definite answer on that, but that is my guess. It sounds like a plausible explanation. Simplicity and eliminating stuff you don't really, that don't add value. Okay. Object attributes. So this would be an example with a class. So it's actually the exact same thing. And you can control both in structs and in classes. You can control access to attributes using the private and the public keyword. So in theory, given that this is a class, I wouldn't have to bother to put private here, because by default, X, Y, Z, and mass would be private anyway, because that's the default for class. If this were a struct, and I would like to make these private, I'd have to put the private keyword here. So what I typically do is just not rely on the defaults. If something is private, I declare it as such. If something is public, I declare it as such. Just to make it really, really clear, this is my intent. Okay, so now, if I declare something private, if I declare attributes private, that means that these members, these attributes, can be accessed from any code within that class or within that struct, but not from the outside. So that's basically the idea. So if I create a particle P later on, and I want to access X underscore, compiler is going to say, no, this is private attribute, you can't touch this. So that's the idea of access control. That's something that you can do in part in Fortran that you can't do in Python. In Python, you don't have the idea of private attributes, private methods. That just does not exist. You have a convention, that's it. Okay. Of course, attributes can also be public. But that means that anyone can change it, anyone can access it. That may or may not be desirable. It depends. Okay, and of course, attributes in general determine the state of objects. That's the idea. So that is how that works. Structs and classes can also define methods. So those are functions that operate on such an object. So on a particle in this case. So for instance, there is a public method, and that is actually a setter. So basically, this allows me to, sorry, a getter in this case. So this allows me to get the value of X. So this is a function with name X. It doesn't take any arguments. It returns a double. And it's not going to change the object. That's why the const is here. And it will return X underscore. So my attribute X underscore is private. The only way to get the X value is through this function. So I can do, I have particle P, I've initialized it somehow, P.X round brackets, is going to give me the x coordinate. So this is a read-only attribute in the sense that the only thing I can get is the value of the x coordinate. I cannot change it directly. Okay, so this is read-only as an attribute. Essentially, private attribute, public getter. Okay. Why would I want to do that? Well, let me give you a slightly different example, because for a particle, well, okay, no, I can give you an example for a particle. Okay, so my particle has a number of attributes. One of them is mass. Okay, I could make mass public. No problem. But that would mean that if I assign a negative value to the mass, everything's fine. Well, probably not, but from the point of view of the compiler, everything's fine. Can do that. Okay, so maybe I want to guard against this. So what I can do is make mass private, create a public getter to get the value, the current value, and create a public setter, so a function that changes the value. Okay, but that function is going to check whether the value you give as a parameter is actually positive. If it's not positive, it's going to generate an error. Okay, so that would be a use case for why I might want to make mass private with both a public getter and setter. The getter is just giving you the value, nothing happens. The setter is going to verify whether the value you want to assign actually makes sense. Okay. So to translate this into Python terms, this would be property. So the property decorator and the value setter decorator for the getter and the setter respectively. Okay, so that's the same semantics. Here you just do that using public, private, judiciously, so that you can control access yourself. Okay, so these are pretty straightforward functions. This is a more interesting one. So this one is going to move the particle some distance in the x, y, and z direction. Okay. So basically, as you can see, this is just a decorator. And of course, this is going to modify the particle. So this is not declared const. If I would put a const here, and the implementation would change the particle, then of course the compiler would say, no, you can't do that. You said you weren't going to change the particle, and you do, so you can't. Okay. So basically, these functions, which we typically call methods, just a fancy name for a function defined in a struct or a class, those are methods, and they are called on an instance. And they can also be private. So here's an example. Sorry, this is a constructor. There's no example. That's stupid. I better have an example. Anyway. Another thing which you typically define in a struct or a class is a constructor. And that's essentially just a way to initialize a new object of that type. So a new variable of that type. Okay. If that reminds you of the dunder init in Python, it's similar. It's not the same, but it's at least similar. So basically it allows you to initialize. So here in this case, this is my constructor. So as you can see, the constructor has the same name as the struct, or in this case, the class, I think. And it takes a number of arguments, the coordinates of the particle, the mass, and the charge, and it's going to initialize those. using these values in order to initialize the private, in this case, attributes. So in this case, the constructor is fairly trivial in the sense that it just assigns each of the parameters to the corresponding private members, to the private attributes. That's the thing it does. So the syntax is a little bit weird. You have no return type, because that's sort of automatic. You have the name, which is always the same. It's the name of the struct. Then you have a normal parameter declaration. That's the same as always. You have the body of the constructor, which is here. So in this case, empty curly brackets, so nothing is explicitly done. And you have something that you don't ever have with other functions. You have this part after the semicolon and before the body. And that is the initializer. So this is just used for initializing attributes. That's the only thing it can do. Yeah.
Similar functionality is the double underscore init function.
It is somewhat similar. The difference is that the init function is literally an initialization function. It's not a constructor. So at the moment the init function is called, the object already exists, while the constructor actually constructs the object. So prior to calling the constructor, the object does not exist. It comes into being at the moment you call the constructor. While in Python, the object is somehow created, and then the init function is called on that object. It's a subtle difference, which doesn't really matter from the viewpoint of C++, but sometimes in Python that can lead to surprises, let's put it that way. If you don't realize that it's not a constructor, but an initialization function. Anyway, this is a true constructor, so this will instantiate a new particle. Okay. So this is just trivial attribute initialization. You can do more sophisticated things there. And of course, in some circumstances, you will also have quite a bit of code in the body of the constructor. Not in this case, because this is a trivial, a fairly trivial data structure, actually. Okay. So, in summary, we have constructors. So they create new objects. You have inspectors, so that allows you to look at the state of your object. They don't change the state of the object. That's why they're called inspectors. They only query. And then you have mutators. They do change the state. So in our running example, we had the particle constructor. We had an X, a Y, a Z, a mass, a charge inspector, and we had a move mutator. Okay. And then there is a last thing, which is a destructor. Trivially, the destructor is generated by the compiler for you. You don't have to do it explicitly, unless. And we'll talk about the unless for quite a while, since that's a pretty non-trivial part of C++. But for simple classes such as these, don't ever write your own destructor. Compiler is going to do it for you. It's going to do it much better for you. So basically, you don't have to bother. Okay. Right. Let's stop here, because basically it's 1 o'clock. It's an unfortunate point to stop, but yeah, I mean, we shouldn't exceed the time limits too much, so I end up already over the time limit. Okay, so we'll continue here tomorrow. Are there any questions at this point? Tomorrow I will also live code this a little bit, then it's less abstract and I can show you better what happens. Yeah, question?
Can you also overload constructors?
You can overload constructors. And in the STL, mostly they are overloaded to death. Yeah. So you can definitely overload constructors. But again, based on the types of the parameters. Or also the number of parameters. Other questions? All right.
Can you recommend a teaching resource to familiarize myself with the syntax, I guess, kind of like an entry level, something like I'm coming from Python, for example. Are there any resources that you've heard about? Or
Well, basically, so basically the question is there sort of a cheat sheet coming from Python to C++? I don't know of any. It must exist, but no, I can't recommend anything because I don't know. But it's actually a very good point. Now there is a resource somewhere. I think it's called Rosetta Code. Yeah, so you probably know the Rosetta Stone, which is something out of archaeology, which was basically a stone containing texts in Greek, hieroglyphs, and forgot what the third language was. Doesn't matter. One language was known, the others were not, and basically the archaeologist was able to decipher hieroglyphs using the Greek, which he knew. So basically that's a Rosetta Stone. So basically it's used as a moniker for something that allows you to easily translate between languages. And Rosetta Code is a project that gives you lots and lots of problems solved in many different programming languages. So basically you have problem X solved in Python, in C++, in C, in whatever. So that might be something to look at, might be interesting, because they probably have fairly simple things like, okay, illustration of a for loop, illustration of a while loop, that kind of thing.
Thank you.
Yeah. Other questions? No? Okay. Then I'll see you tomorrow. Remember, it will be room A rather than room C, and then I can walk around again, which is great. Okay. Enjoy the rest of your day. See you.